So, here's something that might settle gently in your mind as you lie there in the dark. Right now, in the quiet room around you, tiny messengers are landing on your skin. They have been traveling since long before you were born, some of them, bouncing softly off the moon, or the lamp on your ceiling, or a star that might not even be there anymore. A star that may have faded into nothingness long ago, even though its light is still arriving here, still completing its long journey, still reaching you in this exact moment. Your eyes are built to catch these messengers. Your skin is warmed by them, even now, even in the dark. A quiet, gentle warmth that you probably don't even notice anymore, because it has been there your whole life. And here is the strange part, the part that feels like it should not be true but is. You have never once, in your entire life, actually touched one of these messengers. Not once, not ever. Tonight we are going to walk through all of light, explained as simply as possible, because the simplest way to say a thing is usually the truest way to say it. We will start at the very beginning, back before anyone had a word for light at all, back when the whole idea of light was still a complete and total mystery, sitting there in front of everyone every single day but completely unexplained. We will follow the people who spent their whole lives trying to catch it, trying to weigh it, trying to bend it, trying to understand what it actually is at its core, what it is made of, why it behaves the way it does. And by the time we reach the end, you will understand what light really is, how it moves from one place to another, why it carries color inside itself, why your eyes work at all, and how this same quiet thing that is filling the room around you right now, this same gentle presence you cannot see, but that is absolutely everywhere, also carries the internet across oceans, holds entire galaxies together through the long, slow pull of gravity, and lets plants eat sunshine for breakfast every single morning. If you fall asleep somewhere along the way, that is perfectly fine. More than fine, actually. That is part of the point. You do not have to hold on to any of this. You do not have to memorize anything or remember anything or even try to follow every single thread. Just let it drift past you like warm water, like the feeling of a bath when you are very tired and the water is exactly the right temperature and you do not need to do anything except float. The ideas will still be here if you want to come back to them later, and if you do not, that is all right too. Light has been patient for 14 billion years. It has waited through the formation of galaxies and the birth of stars, and the long, slow cooling of the universe into something that could eventually hold life. It can wait for you a little longer. So let us go back, way back, further back than you would expect, further back than any written word or any carved stone or any memory passed down from parent to child. Before anyone had microscopes or telescopes or even good glass to look through, people were already asking a very simple question, a question so simple that a child could ask it, and it turned out to be one of the hardest questions humans have ever tried to answer. The question was this: when you see something, when you look at a tree or a face or a flame, what is actually happening in that moment? Is something coming out of your eyes and touching the thing you are looking at? Or is something coming out of the thing itself and traveling into your eyes? Which direction does the seeing go? It sounds like a silly question now that we know the answer. The way asking whether the sun comes up because it wants to sounds silly to us today. But for almost 2,000 years, some of the most thoughtful people alive genuinely believed that seeing worked like a little flashlight built into your eyes. In ancient Greece, a group of thinkers called the Pythagoreans, working around the 5th century before the Common Era, imagined that our eyes sent out something like invisible feelers, quiet beams that reached out and touched objects the way your fingers reach out and touch a blanket in the dark. That was their answer to how sight worked. Your eye was the flashlight. The world was just sitting there, passive and still, waiting to be scanned by your reaching beams. A little later, another Greek thinker named Empedocles softened this idea slightly. He imagined that the sun and fire gave off something too, some kind of emanation of their own, and that seeing was a meeting in the middle. Your eye's beam would go out, the world's fire would come in, and the two would shake hands somewhere in the space between you and the object. It is a strange picture to hold in your mind now, but you can see the logic that led there. If you close your eyes, the world disappears from your view entirely. It felt natural to think your eyes were doing something active, something intentional, reaching outward, rather than simply receiving whatever happened to arrive. The feeling of looking at something feels active. It feels like you are directing your attention outward, aiming it, and so the idea that something was literally leaving your eyes and traveling to the object made a kind of intuitive sense. Then came Euclid, the same Euclid who gave us the rules of geometry that people still learn in school today, sometime around 300 years before the Common Era. Euclid took the I-beam idea and made it mathematical. He described sight using straight lines shooting out from the eye in a cone shape, spreading wider the further they traveled. And he used this geometric model to explain why things far away look smaller than things close up, and why you cannot see around corners, because the straight beams from your eyes cannot bend. His geometry was actually correct. The geometry of straight lines traveling from the eye outward matched a lot of what people actually experienced when they looked at the world. His picture of light, the direction it was traveling, was backwards. But because his math worked so well for describing what you could and could not see, the I-beam idea stuck around for centuries, wrapped in the credibility of real mathematics, taught and retaught by people who trusted the geometry more than they questioned the underlying direction of travel. It took a very different kind of mind to notice the mistake, and that mind belonged to a man born in the city of Basra, in what is now Iraq, near the end of the 10th century. His name was Ibn al-Haytham, sometimes known in the West by the Latinized name al-Haytham. He is, in a very real sense, the grandfather of the science of light, the person who first asked the question in the right way and then actually tested the answer instead of just thinking about it. And almost nobody learns his name in school, which is worth fixing tonight, worth letting settle into your mind as you lie there, because his story is a quiet one and it deserves to be known. Ibn al-Haytham did something that seems obvious now, but was genuinely radical in his time. He tested the idea instead of just arguing about it. He looked for evidence. He noticed something very simple that anyone could have noticed, but nobody had thought to treat as a clue. If your eyes were sending out beams to touch things, then looking directly at a blazing hot fire or the bright sun should not hurt. After all, your hand does not burn just by reaching toward a fire from a distance. The reaching itself is painless until you get close enough for the heat to travel into your skin. But looking at the sun does hurt, immediately and sharply. You do not have to be close to it. You just have to look at it, and the pain arrives in your eyes the moment the light does. That single careful observation was a crack in a 2,000-year-old idea. Something had to be coming into the eye, not going out of it, and whatever that something was, it was strong enough to cause real physical pain. He built on this observation with more careful reasoning, more patient tests. He studied how light behaved with mirrors, with lenses made of curved glass and polished crystal, and with a simple dark box that had a small hole in one side, a device now called a camera obscura, which is Latin for dark room. If you have ever seen sunlight pass through a tiny gap in curtains and land, as an upside-down glowing patch on the far wall, you have seen exactly what Ibn al-Haytham studied and wrote about in enormous mathematical detail. He poured years of his life into this work, and he eventually gathered all of his findings into a massive text called the Book of Optics, completed in the early 11th century. In that book he proved, using careful diagrams and calm step-by-step reasoning, that light travels from objects into the eye in straight lines, and that the eye is a receiver, not a projector. The eye catches light, it does not send anything out. This is worth sitting with for a moment, in the dark, with your own eyes closed or nearly closed, as you lie there letting the words wash over you. Everything you have ever seen, your mother's face, the ocean, the screen you might have been looking at earlier tonight, all of it arrived at your eyes. You did not reach out for any of it. You did not send anything toward it. It came to you, uninvited, traveling across whatever distance separated you from it, moving in a straight line through the air, until something in your eye caught it and turned it into a picture in your mind. Every face you have ever loved, every landscape that has ever made you pause and breathe a little slower, every word you have ever read, all of it was light arriving, not you reaching. Ibn al-Haytham figured this out using nothing but logic and careful experiment, nearly 1,000 years before anyone had a proper microscope, before anyone knew what cells were, before anyone had mapped the inside of the human eye in any detail. He simply thought about it clearly and tested his thinking against the real world. His work eventually traveled to Europe, translated into Latin over centuries of slow scholarly exchange, and it shaped the thinking of people who came long after him, including a monk and scientist named Roger Bacon in the 13th century. Bacon read Ibn al-Haytham's work carefully, studied it, absorbed it, and became fascinated with a different, very practical question. If light bends when it passes through curved glass, could that bending be used on purpose, to help someone see better? Bacon experimented with curved pieces of polished crystal and glass, placing them over text, noticing that the letters appeared larger and clearer underneath the curve. He wrote about this finding for the Pope of his time, hoping it might help elderly scholars whose eyes had grown tired with age, whose ability to read had faded as their bodies grew older. It would still be a few more decades before craftsmen in northern Italy, likely in the city of Pisa or nearby Venice, worked out how to grind glass into proper lenses and mount them in frames close to the eyes, producing the very first eyeglasses, sometime near the end of the 13th century. For the first time in human history, a person whose own eyes had grown weak, whose vision had blurred with age or strain, could simply put on a small device and see clearly again. A piece of bent light, quietly extending a human life's ability to read, to sew, to work, to recognize a face across a room. Light, bent through shaped glass, giving someone back a piece of their world. Centuries later, this same idea of shaping glass to control light led to something even more dramatic. Around 1608, a spectacle maker in the Netherlands named Hans Lippershey figured out that lining up two lenses inside a tube could make faraway objects appear much closer, as though they had been pulled right up to your eye. Word of this device, the first telescope, spread quickly across Europe, moving from city to city, from workshop to workshop. Galileo Galilei heard about it within the year, built his own improved version, and pointed it at the night sky. He became one of the very first humans to see the mountains and craters on the moon, not as abstract ideas, but as actual physical terrain. He saw the moons circling Jupiter, small bright points that moved night after night in a pattern that made sense only if they were orbiting the giant planet. He saw the countless faint stars of the Milky Way that had always been there, simply too dim and too far for the naked human eye to gather enough light to notice. Light, gathered and focused by shaped glass, was suddenly showing humanity things that had been hidden in plain view for all of history. A German astronomer named Johannes Kepler, working around the same period, took the mathematics of lenses even further. He published detailed work explaining precisely how the eye itself forms an image, correctly describing for the first time that the image projected onto the back of the eye is actually upside down, and that it is the brain, not the eye, which quietly flips it back the right way round before you ever notice anything is happening. Your eye catches the light, projects a tiny upside-down picture onto the back wall of your eyeball, and your brain, without you ever asking it to, without you ever being aware of it, turns that picture right side up and presents it to you as the world. Kepler also improved the telescope design itself, and his refinements are still, in their basic principle, echoed in some telescopes built today, 400 years later. A little later still, the French thinker René Descartes, in the 1630s, worked out a precise mathematical law describing exactly how much any given ray of light bends when it crosses from one material into another, a rule now called the law of refraction. Descartes' version of this law is still taught to students today, sometimes under the name Snell's law, after a Dutch astronomer, Willebrord Snellius, who had worked out a very similar relationship a little earlier, but published far less about it. Between Ibn al-Haytham's proof that light travels into the eye, Bacon and the lens makers turning that bending into eyeglasses, Lippershey and Galileo turning it into a telescope that could reach the moons of Jupiter, and Descartes turning it all into precise mathematics that could be written down and shared and taught, light had gone, in roughly 6 centuries, from a total mystery to something humans could bend, shape, and calculate on purpose. But there was still a huge unanswered question sitting underneath all of this. Everyone now agreed that light traveled from things into your eyes. But what actually was light? Was it a kind of stuff, tiny invisible balls flying through the air? Or was it more like a ripple, the way sound is a ripple moving through air, or the way a wave moves across the surface of a pond when you drop a stone into it? That question, what light actually is at its core, what it is made of, would take another 600 years to even begin to answer properly. And answering it would require people to build tools sensitive enough to catch something that moves faster than anything else in the entire universe. That is where we will go next, but not yet. For now, just let this first part settle. The long, slow arc from wondering whether your eyes reached out like hands, to knowing that light arrives, travels, bends, and can be caught by shaped glass. It is enough for now. Let your breathing stay slow. Let the dark room hold you. There is more to come, but there is no rush. Light is patient, and so is this night, and so are you. Which brings us to the problem that actually needed solving, once people accepted that light travels from objects to the eye. Because agreeing that light moves is very different from understanding what is moving, and how fast, and in what shape. It is one thing to say that light arrives, that it travels across space and enters your eye. It is another thing entirely to say what light actually is, what it is made of, and how quickly it makes the journey. And those questions turned out to be far harder than anyone expected. Think about how strange this problem actually is. If light is a kind of stuff, tiny particles zipping through space like little grains of sand shot from a glowing object, then it should behave a certain way. It should bounce off things sharply, cleanly, the way a tiny ball bounces off a hard wall. It should travel in perfectly straight lines and cast sharp, clear shadows. That picture makes a lot of intuitive sense. It matches what we see when we look at a shadow on the ground or a beam of sunlight coming through a window. It feels right. But if light is a kind of wave, a ripple moving through some invisible medium, then it should behave in a completely different way. It should spread out as it travels. It should bend around the edges of obstacles, the way ocean waves bend around the corner of a pier. It should interfere with itself, producing patterns of adding and canceling the way ripples do when 2 stones are dropped into a pond near each other. These are 2 entirely different pictures of reality, 2 completely different ways of imagining what light might be. And for most of human history, nobody had a way to tell which one was true. The reason nobody could tell was simple. Light moves too fast and too smoothly for the naked eye to catch it doing anything that might give the answer away. You cannot watch a beam of light and see whether it is made of particles or waves. It just looks like light. There was also a much more basic mystery hiding underneath this one, a question so fundamental that it had to be answered before anyone could even begin to sort out the particle versus wave debate. The question was this: does light even take time to travel anywhere at all? Or does it simply appear everywhere at once, the instant a candle is lit or the sun rises above the horizon? This sounds like an odd thing to wonder about now, but remember, in those earlier centuries, nobody had stopwatches accurate enough to measure something moving that fast. Nobody had instruments sensitive enough to catch a delay. And light seemed, to the naked eye, to be completely instantaneous. You strike a match in a dark room, and the whole room is lit, immediately. There is no pause you can notice. No tiny gap of darkness between the striking of the match and the arrival of the light. No sense of something traveling toward you across the space. It just happens. The light is simply there, filling the room, as though it had been waiting to appear. This feeling of instant arrival was so strong, so convincing, that for a long time most people simply assumed light did not take any time at all to get from one place to another. It was just a property of the world, like the fact that objects have weight or that water is wet. You did not ask how long it took for an object to have weight. It just did. Light, people thought, was like that. It just was. The Italian scientist Galileo Galilei, early in the 17th century, actually tried to test this directly in one of the more quietly charming failed experiments in the history of science. He wanted to know if light had a speed, and if so, what that speed might be. So he designed a simple test. He stationed two people on distant hilltops at night, each one carrying a covered lantern. The first person would uncover their lantern, letting the light shine out across the dark valley. The second person, standing on the far hilltop, would watch for that light, and the moment they saw it, they would uncover their own lantern in response. Galileo planned to measure the tiny delay between the first flash and the answering flash, and from that delay, and the known distance between the two hills, calculate how fast the light had traveled. It did not work, not because the idea was foolish, and not because the logic was wrong. The idea was perfectly sound, the logic was correct. It did not work because light moves so unbelievably fast that the delay between the two flashes was far, far smaller than any human reaction time could ever hope to detect. The fraction of a second it took for the light to cross the valley was swallowed up completely by the much longer time it took for the second person to see the light and move their hands to uncover their own lantern. Human reflexes were simply too slow to measure something that fast. Galileo understood this. He concluded, quite reasonably, that light traveled extremely fast, so fast that it might as well be instantaneous for any practical human purpose, and he left the actual measurement for someone else, someday, with a better trick. That someday came in 1676, and the better trick came not from a laboratory on Earth, but from watching one of Jupiter's moons, far out in the cold darkness of the outer solar system. A Danish astronomer named Ole Rømer was working at the Paris Observatory, carefully timing the eclipses of Io, one of the 4 large moons circling the giant planet Jupiter. These were moons that had been spotted decades earlier by Galileo himself, the first moons ever seen orbiting another world. Io circles Jupiter regularly, faithfully, like a tiny clockwork mechanism, disappearing into Jupiter's shadow at predictable intervals and then emerging again on the other side. Astronomers had been timing these eclipses for years, and they knew the schedule well. Rømer noticed something odd in his data, something that did not fit the simple, regular pattern everyone expected. When Earth was on the same side of the Sun as Jupiter, relatively close to the giant planet in their shared journey around the Sun, the eclipses of Io happened almost exactly on schedule, right when they were supposed to. But when Earth had moved around in its orbit to the far side of the Sun, much farther away from Jupiter, the eclipses were consistently late. Not late by a tiny amount that could be ignored or blamed on a clock error, late by several minutes. Again and again, every time Earth was on the far side. Rømer realized what this meant. It was not that Io's orbit was changing. Io was still circling Jupiter at its usual steady pace, completely indifferent to where Earth happened to be. The change was not happening out at Jupiter. The change was happening in the time it took for the light carrying the news of the eclipse to travel from Jupiter all the way to Earth. When Earth was farther away, that distance was longer, and the light simply had more space to cross. That extra distance took extra time. Light was not instantaneous after all. It had a speed, a real and measurable speed, and the delay Rømer was seeing was just the light taking a little longer to complete a longer journey. By comparing the timing differences with the extra distance Earth had traveled in its orbit, Rømer produced the very first real estimate for the speed of light. He used nothing but a telescope, a clock, and years of patient watching, noting down eclipse times night after night, season after season. His number was not perfectly accurate by modern standards. The distance across the solar system was not yet known precisely enough for that, but it was in the right neighborhood. It told scientists, for the first time in human history, that light takes time to get anywhere, that it is not magic, that it is a traveler, moving through space at a particular pace, like everything else in the universe. This means something quietly lovely when you stop to think about it. Even the light from the sun hitting your face on a warm afternoon is about 8 minutes old by the time it arrives. The sunlight touching your skin left the surface of the sun 8 whole minutes before you felt it. If the sun were to suddenly go dark, which it will not, but if it did, you would not know for 8 minutes. You would still see it shining in the sky, still feel its warmth on your arms, for 8 full minutes after it had stopped shining, because the light that was already on its way would still be traveling toward you, crossing that long, quiet stretch of space between the sun and earth. You are always looking very slightly into the past. Every glance at the sun, every shadow cast on the ground, every sunbeam coming through a window is a message that left its source 8 minutes ago. Romer's number, useful as it was, still relied on distances across the solar system, numbers that were themselves only roughly known at the time. The size of Earth's orbit was not yet pinned down with great precision, so any calculation that depended on that size was going to carry some uncertainty. It took almost 200 more years before anyone managed to measure the speed of light using nothing but equipment sitting entirely on a tabletop right here on Earth, without needing to know the distance to Jupiter or the width of the solar system at all. In 1849, a French physicist named Hippolyte Fizeau set up a clever contraption in Paris. He sent a beam of light out through the gaps of a rapidly spinning toothed wheel, aiming it toward a mirror placed several miles away on a hilltop in Montmartre. The light would pass through a gap between the teeth of the spinning wheel, travel all the way to the distant mirror, bounce off it, and travel back toward the wheel. If the wheel was spinning at just the right speed, the returning beam of light would arrive exactly as the next tooth had rotated into place, blocking the light from passing through. The light would disappear. By measuring exactly how fast the wheel needed to spin for the returning light to be blocked, and knowing the exact distance to the mirror, Fizeau could calculate the speed of light with remarkable accuracy. His value was very close to the true number, and for the first time, the speed of light had been measured entirely with Earth-based equipment, in a setup a person could build in a workshop and set up across a few miles of countryside. A colleague of Fizeau, a physicist named Léon Foucault, refined the method shortly afterward. Instead of a toothed wheel, Foucault used a spinning mirror, which allowed for even more precise timing. He pushed the accuracy even further, narrowing in on a number that scientists could trust. Between Roma watching a distant moon, Fizeau timing light across the rooftops of Paris, and Foucault refining the method with a spinning mirror, humanity had finally pinned down the speed of the fastest thing in the universe. Light moved at roughly 186,000 miles every single second, a number so large it barely fits in a human mind used to walking speeds and the pace of a cart or a horse. At that speed, light could circle the entire Earth about 7.5 times in the time it takes you to draw a single breath. This was the problem that needed solving, laid bare and finally answered. Light moved and moved faster than anything anyone had ever imagined, but it was not instant. It had a nature, it had a speed. It could be timed, first across the vast dark spaces of the solar system, by watching a moon of Jupiter wink in and out of shadow, and later across a few miles of Parisian countryside, using a spinning wheel and a distant mirror. And once people knew that light could be measured this precisely, once they had a number they could write down and check and refine, they wanted to know everything else about it too. What was it made of? What was its shape? How did it carry color? How did it bend? That deep curiosity, that need to understand the thing they had just learned to measure, is what led to the first real breakthrough in understanding what light actually was at its core. The breakthrough we will walk through next. But for now, just let this part settle. Light travels. It has a speed. It takes time. The sun you see is 8 minutes old. The stars you might glimpse through a window are years or centuries or millennia old by the time their light reaches your eyes. You are always, in a very gentle and very real way, looking back in time. Let that thought rest with you in the dark. There is no rush. The light is still traveling, and so is this night, and so are you. The first great breakthrough in understanding what light actually is made of belongs mostly to one restless English mind, though as with most breakthroughs, other people were circling the same ideas around the same time, in different countries, in different languages, each one turning the problem over in their own way. Isaac Newton, in the late 1660s, while Cambridge University was closed because of an outbreak of plague, spent long stretches of time alone at his family's house in the countryside, doing some of the most important thinking of his life. He was a young man then, barely into his 20s, with no professors to guide him, no colleagues to argue with, just the quiet of the countryside and the inside of his own head. Among many other things he thought about during those long quiet months, he became obsessed with a simple triangular piece of glass called a prism. Everyone at the time knew that a prism could take ordinary white sunlight and spread it out into a strip of rainbow colors: red, orange, yellow, green, blue, violet. It was a familiar trick, a parlor curiosity, something you might see at a fair or in a gentleman's study. But nearly everyone believed that the glass itself was somehow adding color to the light, staining it the way a stained glass window colors a beam of sun passing through it. The light went in white and came out colored, so the natural assumption was that the glass was doing something to the light, mixing something into it, changing it in some way. Newton was not satisfied with this assumption. He wanted to test it, to see if it was really true. So he set up a careful experiment in a darkened room with a single small hole, letting in one narrow beam of sunlight. He let that beam pass through a prism, spreading it out into the familiar rainbow band on the far wall, just as everyone had seen 100 times before. But then he did something clever, something nobody had thought to do before. He took a second prism and placed it in the path of just one of the colored beams, say the red one, all by itself, isolated from the rest of the rainbow. If the prism was adding color to the light, then passing red light through a second prism should change it further. It should split it into new colors, or alter it somehow. It did not. The red light stayed red. It simply bent a little more as it passed through the glass, changing direction slightly, but its color never changed. It remained exactly, stubbornly red. From this single careful observation, Newton reached a conclusion that overturned centuries of assumption. White light was not pure and colorless at all. White light was actually a mixture of all the colors already, all bundled together, traveling as one. The prism was not creating color out of nothing. It was sorting a mixture that was already there, the way a sieve sorts different sized stones that were already mixed together in a pile. Each color bent by a slightly different amount as it passed through the glass, red bending the least, violet bending the most, which is exactly why they spread apart into a visible rainbow. The colors had always been inside the white light, hidden, waiting to be separated. Newton even took the experiment one step further. To make the proof as solid as possible, he used a second prism turned the opposite way, catching all the separated colors and gathering them back together, recombining them into a single beam of white light once again. The colors appeared, and then they disappeared back into whiteness. This was the final piece of evidence. The colors were always there, inside the white, waiting to be sorted, and they could be put back together as easily as they were taken apart. White light was not simple. It was a crowd of colors traveling together. This was the first real foundational concept of the science of light, the idea that color is not something added to light by objects or by glass. Color is something already contained within light itself, a built-in property of it. Different colors are simply different flavors of light, bending by slightly different amounts when they pass from one material into another, and as we will see later, vibrating at slightly different speeds, which is the deeper reason for the bending in the first place. But Newton believed something else about light, something that turned out to be only half right. And it is worth explaining clearly because the disagreement it caused shaped the entire next century of science, pulling thinkers into two opposing camps that would argue for generations. Newton believed that light was made of tiny particles. He called them corpuscles, Tiny, invisible balls shot out from glowing objects, flying through space in straight lines, bouncing off mirrors the way a ball bounces off a wall. This picture explained a lot of what light does, and it explained it well. It explained why light travels in straight lines and casts sharp, clean shadows. It explained reflection perfectly, the angle of a bounce matching the angle of arrival, just like a ball bouncing off a flat surface. It felt solid. It felt physical. It felt right. And because Newton was so deeply respected, and rightly so, for his other towering work, especially his laws of motion and his theory of gravity, his particle theory of light became the dominant belief for the better part of 100 years. When Newton spoke, people listened, and for a long time, most scientists simply accepted that light was made of tiny flying particles, because Newton had said so, and because the explanation seemed to fit what everyone could see with their own eyes. But not everyone agreed, and the strongest disagreement came from a Dutch scientist named Christiaan Huygens, working around the same period as Newton in the 1670s and 1680s. Huygens proposed a completely different picture of what light might be. He suggested that light was not made of tiny particles at all, but was instead a wave, spreading outward the way ripples spread outward from a stone dropped into still water. Light, in Huygens' picture, was a disturbance moving through some invisible medium, not a stream of objects flying through empty space. Huygens built an entire mathematical framework showing how wave-based light could explain reflection and the bending of light through glass, called refraction, just as well as Newton's particle idea could. The two pictures, particles and waves, gave the same answers for the basic behavior of light in mirrors and lenses. They just got there by different routes. For Huygens, light needed some invisible substance to ripple through, the way sound needs air to travel through, and he called this invisible substance the luminiferous ether. The word luminiferous simply means light-carrying. It was the substance that was thought to fill all of space, even the seemingly empty parts, providing something for the light waves to wave in. Huygens' wave picture rested on a simple and elegant idea that still bears his name today. It is called Huygens' principle. He proposed that every single point along a moving wavefront acts as though it were its own tiny new source of ripples, spreading outward in all directions, and the overall shape of the advancing wave is just the combined result of all those countless tiny ripples overlapping together. To picture this, imagine a long line of people standing shoulder to shoulder at the edge of a swimming pool, and each one drops a small pebble into the water at the exact same instant. Individually, each pebble makes its own small circular ripple, expanding outward from where it fell. But added together, all those overlapping circles combine into one single straight wavefront, moving forward as a unit, a line of water rising and traveling across the pool. The individual ripples are still there, underneath the surface, but what you see from above is a single clean line. Huygens used this simple picture to correctly predict how light bends when it enters a new material like glass or water, and his predictions matched the same results Newton's particle theory predicted for ordinary reflection and refraction. This is exactly why the argument between the two men could not be settled by those experiments alone. Both pictures, particles and waves, got the basic bending of light right. Both could explain why a mirror reflects at the angle it does. Both could explain why a lens focuses light to a point. They just explained it for different underlying reasons, and for a long time there was no experiment clear enough to say which picture was true. For over a century, these two ideas sat in tension, particles versus waves, two completely different ways of imagining the same thing. Newton's camp generally won out, simply because of Newton's enormous scientific reputation, and because his particle picture handled sharp shadows and straight-line travel a little more intuitively than Huygens' wave picture did at the time. Waves, after all, tend to spread out and bend around corners. You can hear someone talking even if they are around a corner, because sound waves bend around the edge of the wall. But light does not seem to do that. Light casts sharp shadows. Light travels in straight beams. It seemed more like a stream of tiny objects than a spreading ripple. It would take a very simple, very elegant experiment, performed more than 100 years after Newton and Huygens had both passed away, to settle the argument in a way nobody could ignore. And that experiment belongs to the next part of our story, the development of the idea, where the picture of light became richer, stranger, and much closer to what we now understand to be true. But before we leave Newton, it is worth pausing for a moment on what he actually gave us, because it was more than just a theory about particles. He gave us the idea that color lives inside light itself, that the rainbow is not something a prism creates, but something a prism reveals, something that was already there, hidden in the whiteness, waiting for someone patient enough to pull it apart and look at the pieces. Every rainbow you have ever seen, every splash of color cast by a glass ornament in a sunny window, every spectrum spread across a classroom wall, is a direct descendant of that quiet experiment in a darkened countryside room, with a young man, a piece of glass, and a question nobody had thought to ask in quite the right way before. Newton also gave us the question that would drive the next century of inquiry. If light was not particles, what else could it be? He planted the question, even if he did not arrive at the full answer himself. His work stood as a challenge, a clear statement that could be tested and either confirmed or overturned. That is how science moves forward, not by one person getting everything right, but by one person getting enough right that the next person can see what is still missing. Newton got the colors right. He got the bending right. He got the core idea that white light is a mixture, not a pure thing. Those pieces have never been overturned, they have only been added to. So as you lie there in the dark, let Newton's prism sit quietly in your mind for a moment. A simple triangle of glass, held in a sunbeam, pulling apart something that had been traveling together since it left the sun 8 minutes earlier. Red bending a little, violet bending a little more, and every other color finding its place in between. It is a gentle image. It is the kind of image that settles well in a quiet room at night. Light, arriving whole, and then spreading out into its parts, and then, if you wanted to, being gathered back together into whiteness again. Nothing lost, nothing added, just sorted, and then rejoined. Like taking a breath and letting it go. Like closing your eyes and opening them again. The colors were always there, and they are always there, even now, even in the dimmest light around you, waiting inside every beam that happens to pass through a piece of glass, or a drop of water, or the lens of your own eye. That is where Newton left us. With color understood, and with a question still hanging in the air, particles or waves, little balls or spreading ripples, the answer would take more than 100 years to arrive, and when it did, it would come from a man with a piece of card, 2 thin slits, and a single candle flame. But that is for the next part of the story. For now, just let the image of the prism rest with you. White light, full of hidden colors, patient and whole, waiting to be seen. By the early 1800s, a British physician and physicist named Thomas Young decided to test the wave idea directly. He did not build a large machine. He did not need a laboratory full of expensive equipment. He used a piece of card, 2 narrow slits cut close together, and a single candle flame. What he saw when he looked at the screen behind those 2 slits changed the way we understand light forever, and it did so with a quiet simplicity that still feels almost too neat to be true. Imagine the setup in your mind. A dark room, a single light source, steady and small, a piece of card with 2 thin slits, side by side, like 2 tall, narrow windows cut into a wall. Behind the card, a plain screen, just a flat surface waiting to catch whatever light makes it through. If light were made of simple particles, the way Newton had imagined, tiny invisible balls flying in straight lines from the candle flame, then what should appear on that screen is fairly obvious. The particles would stream through one slit or the other, traveling in straight paths, and they would land directly behind each slit. You would see 2 bright stripes on the screen, one lined up behind each opening, and darkness everywhere else. That is what common sense predicts. That is what the particle picture demands. That is not what Young saw. Instead, Young saw a whole pattern of alternating bright and dark stripes, many of them spreading out across the screen, fading in brightness toward the edges. Not two stripes, not a simple pair of glowing lines, a whole fan of light and shadow, repeating over and over, like the ridges on a washboard or the bands of color in a soap bubble. This pattern had a name. It was called an interference pattern, and it was something that only waves could produce. To understand why, think about what happens when two sets of ripples overlap on the surface of a pond. Imagine dropping two small stones into still water, a few inches apart at the same moment. Each stone sends out its own set of circular ripples, expanding outward. Where the peak of one ripple meets the peak of the other, they add together, and the water rises twice as high. That is called constructive interference, two waves reinforcing each other. Where the peak of one ripple meets the trough of another, the raised part and the lowered part cancel each other out, and the water goes flat, as though neither ripple had ever passed through that spot at all. That is called destructive interference, two waves erasing each other. When you shine light through two narrow slits, something very similar happens. The light spreads out from each slit, not as two separate streams of particles, but as two overlapping waves, like the ripples from two stones dropped side by side. Those two waves meet on the far side of the card, and depending on how far each one has traveled to reach a particular spot on the screen, they either arrive in step, peak matched with peak, or out of step, peak matched with trough. Where they arrive in step, you get a bright stripe. Where they arrive out of step, you get a dark stripe. And because the distance each wave travels changes smoothly as you move along the screen, the pattern alternates smoothly too. Bright, dark, bright, dark, bright, dark. A whole sequence of stripes marching outward from the center. This was the signature of wave behavior. It was unmistakable. Young had proven, with a piece of card, two slits and a candle, that light behaves as a wave. The experiment was so clean, so direct, so hard to argue with, that it shifted the entire conversation. Huygens, it seemed, had been right all along, though he had not lived to see his idea vindicated. Light was not a stream of tiny particles. Light was a ripple, spreading and overlapping and canceling and reinforcing, just like waves on water. This single experiment is so elegant that scientists still perform it in classrooms today, exactly as Young did, and it still produces the same striped pattern. The equipment is slightly more modern now, but the principle is identical. Shine a light through two slits, and you see interference. It is one of those rare experiments that is both simple enough for a child to understand and deep enough to have kept physicists occupied for centuries. And as we will see later, it would go on to become even stranger and more important once quantum physics entered the picture many decades later, raising questions that we are still trying to fully answer. Around the same time that Young was shining candlelight through slits in England, other scientists on the European continent were adding new layers to the wave picture. A French engineer named Augustin Jean Fresnel developed detailed mathematics describing exactly how light waves bend around obstacles and spread out after passing through narrow openings. This behavior is called diffraction, and it is something you have almost certainly seen without knowing its name. When light passes through a very small gap, it does not simply continue in a straight, sharp-edged beam. It spreads out, fanning into the shadow that should, according to simple particle thinking, be completely dark. You can see this for yourself if you hold two fingers very close together in front of a bright light and look at the tiny gap between them. The light does not stay strictly between your fingers. It softens at the edges, blurring into the dark, bending into places a straight line should not reach. Fresnel's mathematics explained this softening. It explained the exact angles at which light would bend, the exact brightness of the fringes that would appear, the exact conditions under which diffraction would be visible, and when it would be too subtle to notice. His work reinforced the wave picture powerfully, because diffraction was another behavior that only waves could produce. Particles traveling in straight lines cannot bend around corners. Waves can. The fact that light does bend, even just a little, even just at the very edges of a shadow, was another piece of evidence that the wave picture was the correct one. Between Young's interference pattern and Fresnel's mathematical treatment of diffraction, the case for light as a wave became very strong. Strong enough that the old particle theory, Newton's corpuscles, began to fade from favor. It did not disappear entirely, and we will see later why it made a surprising return in the 20th century. But for the scientists of the early 1800s, the question seemed settled. Light was a wave. But this settlement opened up a new question, a question that was in some ways even deeper than the one Young had just answered. If light is a wave, then what exactly is waving? Sound waves are easy to understand in this regard. Sound is a ripple of air pressure, a compression and stretching of the air molecules themselves, traveling outward from whatever made the noise. Ocean waves are easy too. They are ripples of water, the surface rising and falling as energy passes through. But light can travel through the empty vacuum of space. It crosses the 93 million miles between the sun and the earth, a distance filled with almost nothing at all. No air, no water, no substance you can point to and say, that is what is waving. So what was light a ripple of? For a long time, the best answer anyone could give was the one Huygens had proposed more than a century earlier. Light must be rippling through some invisible substance that fills all of space, even the parts that seem completely empty. This substance was called the luminiferous ether, the light-carrying medium, and it was imagined to be everywhere, filling the gaps between stars, passing through solid walls, permeating everything, unseen and unfelt but absolutely necessary for light to travel. Without the ether, the thinking went, light waves would have nothing to wave in, and they could not exist. The ether was a reasonable idea, given what scientists knew at the time. Every other kind of wave anyone had ever encountered needed a medium. Sound needed air or water or some other material to travel through. Ocean waves needed water. Seismic waves needed rock. It was natural to assume that light must need something too, even if that something was invisible and undetectable by any means anyone had yet devised. But the ether idea came with its own set of problems. If the ether filled all of space, then the Earth must be moving through it constantly as it orbited the sun, plowing through this invisible ocean at tremendous speed. That motion should create a detectable effect. Light traveling in the same direction as the Earth's motion through the ether should behave very slightly differently than light traveling across that motion. The way swimming with a river current feels different from swimming against it or across it. Detecting that difference would be the key to proving the ether existed. The answer to this puzzle, the answer to what light was actually waving in, would come from a Scottish physicist named James Clerk Maxwell in the 1860s, and it would turn out to be one of the most elegant unifications in the entire history of science. But that is for the next part of our story. For now, let Young's quiet experiment rest in your mind: a dark room, a candle, 2 slits in a piece of card, and a pattern of stripes that told us something we had been trying to understand for centuries. Light is a wave. It spreads, it overlaps, it cancels and reinforces. It bends around edges. It behaves not like a stream of tiny bullets, but like ripples spreading across a still pond, overlapping and interacting in ways that particles never could. And yet, as we will see later, the particle idea was not entirely wrong either. It was only waiting for a new century and a new kind of thinking to bring it back in a form nobody could have predicted. The full truth about light is stranger than either Newton or Huygens or Young ever imagined. It is a wave, yes, but it is also something else, something that does not fit neatly into either category, something that required an entirely new branch of physics to describe. But that is further down the road. For now, just let the image of those stripes settle into the quiet of the room. Bright, dark, bright, dark. A pattern made of overlapping ripples, written in light on a plain screen. In a dark room, more than 200 years ago, by a man with a piece of card and a patient, curious mind. The ripples are still traveling. They are still overlapping. They are still making patterns, here and everywhere, whether anyone is watching or not. Light spreading and meeting itself, quietly, endlessly, in the dark. The answer to that question, what light is actually a ripple of, came from a Scottish physicist named James Clerk Maxwell in the 1860s, and it is one of the most elegant unifications in the entire history of science. To understand what Maxwell did, we need to step back for a moment and look at two forces that, up until his time, scientists treated as completely separate things, as different from each other as wind is from stone. The first force was electricity. People had known about electricity in a basic way for a long time. They knew about lightning in the sky. They knew about the strange crackle you might feel from static on a dry day, the way a wool sock pulled from a blanket can make a small spark in the dark. They knew that certain materials, when rubbed, could attract small objects, the way a comb run through dry hair can pick up tiny scraps of paper. Electricity was a curiosity, a phenomenon, something people could produce and play with, but did not deeply understand. The second force was magnetism. People had known about magnetism for a long time too. They knew about lodestones, naturally occurring rocks that could attract iron. They knew about compass needles, which always pointed north, a fact that had guided sailors across oceans for centuries. They knew that magnets could push each other apart or pull each other together, depending on which ends were facing each other. Magnetism, like electricity, was a familiar presence, but its deeper nature was a mystery. For most of human history, these two forces were seen as completely unrelated. Electricity was one thing, magnetism was another. They lived in different parts of the physics books. They were studied by different people using different tools. There was no obvious reason to think they had anything to do with each other at all. But hints of a connection had begun to appear. A Danish scientist named Hans Christian Ørsted, in 1820, noticed something curious during a lecture demonstration. When he ran an electric current through a wire, a nearby compass needle twitched. The electricity in the wire was somehow creating a magnetic effect, reaching out through the air and moving the needle. It was a small observation, a tiny flicker of a compass needle in a crowded room, but it was the first clear sign that electricity and magnetism were not as separate as everyone had assumed. A British experimenter named Michael Faraday, working a few years later, pushed this connection much further. He found that moving a magnet near a coil of wire could create an electric current in that wire, even though the magnet never touched the metal. A changing magnetic field was producing an electric field. The two forces were not just connected. They were somehow generating each other, calling each other into existence under the right conditions. This is where Maxwell entered the picture. He took all of these observations, all of the experiments done by Ørsted and Faraday and others, and he gathered them into a set of 4 equations. These equations were not long or complicated to look at, but they contained a whole world of meaning packed into their symbols. They described, with precise mathematical language, exactly how electric and magnetic fields behave, how they relate to each other, and how they respond to charges and currents. And within those equations, Maxwell noticed something that nobody had quite seen before. He saw that a changing electric field naturally creates a magnetic field. That was Faraday's finding, written in mathematical form. But he also saw that a changing magnetic field naturally creates an electric field. That was the other half, the mirror image. And if both of those things were true, then something remarkable became possible. A changing electric field could create a magnetic field, which would then change and create a new electric field, which would then change and create a new magnetic field, and so on, endlessly. The two fields could chase each other forward through space, each one giving rise to the other, neither one needing any material substance to travel through. They could sustain themselves, a ripple of pure fields, moving outward forever. Maxwell calculated how fast this self-sustaining ripple should travel through empty space. He used numbers that had been measured in laboratories, the known strength of electric and magnetic forces, numbers that had nothing to do with light or optics at all. They came from experiments with magnets and wires and charged plates, not from prisms or lenses or candles. And when he finished the calculation, the number that came out of his equations matched, almost exactly, the measured speed of light. This was not a coincidence. The match was too close, too precise, to be an accident. Light itself, Maxwell proposed, was an electromagnetic wave. It was a ripple of electric and magnetic fields chasing each other through space, needing no ether, no invisible substance, nothing at all, except the fields themselves. Light was not a mysterious separate thing sitting alongside electricity and magnetism, unrelated to the rest of physics. Light was electricity and magnetism, dancing together, moving at a very particular, very fast, very specific speed. This was a unification of a kind that rarely happens in science. Two forces that had seemed completely separate, electricity and magnetism, turned out to be two faces of a single underlying force, now called electromagnetism. And light, the thing that fills our eyes and warms our skin and lets us see the world, turned out to be made of the same stuff as the spark from a wool sock and the pull of a compass needle. Everything was connected, underneath, in a way that nobody had guessed. Maxwell's equations did something else that was just as important. They suggested that visible light, the rainbow Newton had split apart with his prism, was only a small slice of something much larger. If electric and magnetic fields could ripple at the frequency our eyes happen to detect as visible light, there was no reason they could not ripple at other frequencies too. Faster ripples, slower ripples, ripples our eyes were simply not built to see. The equations did not limit the possible speeds of rippling. They just described how the ripples would behave at any frequency. The door was open to a whole invisible world. Not everyone let go of the old ether idea right away. The thought that light could travel through completely empty space, with no medium at all, was difficult to accept. For 200 years, scientists had been picturing light as a wave in some invisible substance. Old habits of thought are hard to release. So even after Maxwell's equations showed that the ether was not necessary, many physicists still believed it must be there, hidden, waiting to be detected. And it took one more famous experiment to close the door on the ether firmly and for good. The reasoning behind this experiment was straightforward. If the Earth was constantly moving through a fixed ether as it orbited the Sun, then a beam of light traveling in the same direction as the Earth's motion through that ether should behave very slightly differently than a beam traveling across that motion. Think of swimming in a river. If you swim with the current, you move faster relative to the shore. If you swim against the current, you move slower. If you swim straight across, the current pushes you sideways. In the same way, light traveling through the ether should show slight differences in speed, depending on which direction it was traveling relative to the Earth's motion through space. In 1887, two American scientists, Albert Michelson and Edward Morley, built an instrument designed specifically to detect this tiny difference. It was an extraordinarily sensitive device, a tabletop arrangement of mirrors and light beams, set up to split a single beam of light into two paths that traveled at right angles to each other. After bouncing off mirrors at the ends of their paths, the two beams were recombined. If the motion through the ether affected the speed of light differently along the two paths, the recombined beams would show a slight shift in their interference pattern, the same kind of bright and dark stripes that Young had used to prove light was a wave. The instrument was sensitive enough to detect a shift far smaller than what the ether theory predicted. Michelson and Morley found nothing, no shift at all, no difference in the speed of light along the two paths, no matter which direction they pointed their instrument, no matter the time of day or the season. They checked and rechecked. They waited months and tried again. The results stayed the same, a complete absence of the expected effect. This became one of the most famous null results in the history of science. A null result is when an experiment finds nothing, and usually that is not very exciting. But this particular nothing was deeply meaningful. It quietly confirmed what Maxwell's equations had already implied. Light needs no ether at all. Its speed through empty space is simply a fixed, built-in property of the universe itself, not something measured relative to some hidden background substance. The speed of light is the same for everyone, no matter how fast or in what direction they happen to be moving. This puzzling constancy of light's speed would go on, a couple of decades later, to become one of the central building blocks of Einstein's theory of relativity, which changed how we understand space and time themselves. But that is a story for another night. For now, what matters is what Maxwell's unification gave us. It gave us a true answer to the question of what light actually is. Light is a ripple of electric and magnetic fields, moving through space at a fixed speed, needing no medium, carrying energy from one place to another. And it gave us something else too, something that opened up the whole rest of the story. It told us that visible light, the narrow slice of the rainbow our eyes can detect, is just a small part of a much larger family. If electric and magnetic fields can ripple at the frequencies we see as red and green and blue and violet, they can also ripple at slower frequencies and faster ones. Slower than red, faster than violet. Our eyes did not evolve to see those other ripples, but they are there, all around us, all the time. The visible rainbow is just a small window in the middle of an enormous invisible landscape. On one side of that window lie radio waves, microwaves, and infrared light. On the other side lie ultraviolet light, X-rays, and gamma rays. All of them are the same fundamental thing, ripples of the same fields, traveling at the same speed, differing only in how tightly packed their ripples are. This whole extended family is called the electromagnetic spectrum, and we will walk through it more slowly later. But for now, just let the idea settle. Light is not alone. It is part of something much bigger, a quiet ocean of electromagnetic waves that fills the room around you, passing through you, carrying signals and warmth and information, most of it completely invisible, completely silent, completely unnoticed. Maxwell himself did not live to see all of the consequences of his equations. He died in 1879, at the age of 48, before the Michelson-Morley experiment, before Einstein, before radio, before X-rays, before all the technologies that would grow out of his quiet mathematical work. But he had given the world a gift. He had shown that light, electricity, and magnetism are one thing, not three. He had written down the rules that govern how that one thing behaves, and he had opened the door to everything that came after. So as you lie there in the dark, let Maxwell's ripple rest in your mind. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They chase each other forward endlessly, needing nothing but themselves. That is what light is. That is what has been traveling across space to reach you. From the lamp on the ceiling, from the moon outside your window, from stars that may have died before the earth was born. Electric and magnetic fields, dancing together, moving at a speed that never changes, bringing warmth and color and information, silently, constantly, to the back of your eyes. The same force that moves a compass needle is the force that lets you see the face of someone you love. Everything is connected, underneath, in a way that is quiet and deep and true. Let that thought settle. There is no rush. The fields are still dancing, and so is this night, and so are you. Now, before we go further, let us slow everything down completely. If you are still with me, let your eyes close now if they are not already. You do not need to follow every word from here. Just let it wash over you, the way the light from a street lamp washes gently over a curtain in a quiet room. The explanation continues either way, whether you are catching every word or drifting somewhere between waking and sleep. There is no test at the end. There is nothing you need to remember. Just let the words come and let them go. Let us talk now about how light actually works, the real mechanics underneath everything we have covered so far. Because once you understand the mechanics, once you see the simple moving parts underneath, everything else about light starts to make sense on its own. The history, the experiments, the arguments between Newton and Huygens, the equations Maxwell wrote down, all of it snaps into place when you understand what is actually happening at the smallest level. Here is the simplest true way to say what light is. Light is a ripple of electric and magnetic fields moving through space. That is it. That is the whole thing, stripped down to its core. And different colors of light are simply different speeds of rippling, which scientists call frequency. The color of light is just how fast the ripple is shaking. To picture this, imagine holding one end of a long jump rope and your friend holds the other end, far away across a field. If you shake your hand slowly, up and down, you create a slow, wide ripple traveling down the rope. The bumps are far apart. The rope rises and falls in long, gentle waves. If you shake your hand very quickly, much faster, you create a fast, tight ripple, with the bumps much closer together, marching down the rope in quick succession. The rope itself has not changed. It is the same rope held by the same two people, only the speed of your shaking hand has changed, and that changes the shape of the ripple traveling along it. Light works the same way, except instead of a rope, it is empty space itself that is rippling with electric and magnetic fields. And instead of your hand shaking, it is tiny charged particles, usually electrons, inside atoms, jiggling around, starting the ripple in the first place. A slow, wide ripple of light, one with a long distance between each wave crest, appears to our eyes as red. A fast, tight ripple, with wave crests packed closely together, appears to our eyes as violet. Every color in between, orange, yellow, green, blue, is simply a rippling speed somewhere between those two extremes. This rippling speed is called wavelength when we measure the physical distance between one crest and the next, the space between one bump and the one following it. It is called frequency when we measure how many ripples pass a fixed point every single second. They describe the same thing from two different angles, two ways of talking about the same underlying reality. A long wavelength means a low frequency, fewer ripples passing per second. A short wavelength means a high frequency, more ripples passing per second. And these two measures are always tied together, locked in a fixed relationship, because all light, no matter its color, no matter its wavelength, travels through empty space at exactly the same speed. That speed, as we have already heard, is roughly 186,000 miles every single second. In an hour, light travels about 670 million miles. These are numbers so large they barely make sense to a human mind, used to cars and footsteps and the slow pace of a walk across a room. At that speed, light could circle the entire Earth about 7.5 times in a single second. In the time it takes you to breathe in once and breathe out again, a beam of light could travel from the Earth to the Moon and most of the way back. Now here is where the invisible part of the rainbow comes in, the part that Maxwell's equations opened up for us. Our eyes only detect a very narrow slice of all the possible rippling speeds that electromagnetic waves can have. The full range is enormous, stretching far beyond what we can see in both directions, and we sit right in the middle of it, seeing only a thin band of the whole. Slower than red light, with even wider gaps between wave crests, is a whole invisible world our eyes cannot see at all. Slightly slower than red is infrared light. You cannot see it, but you can feel it, as warmth on your skin. This is why the heat from a fireplace or a warm mug reaches you even in total darkness. The light is there, traveling from the warm object to your skin, but your eyes are simply not built to notice it. Your skin notices it instead. Slower still is microwave radiation. This is the same kind of light used inside a microwave oven, where it gently jostles water molecules in food until they heat up, warming your meal from the inside. And it is also the same kind of light used to carry phone calls and Wi-Fi signals through the air around you right now, silently crossing the room you are lying in, passing through walls and blankets and through you, constantly, without you feeling a thing. Slower still, with the widest ripples of all, are radio waves. These are the waves that carry music into a car radio, stretching sometimes for the length of a football field between one wave crest and the next. Huge, slow ripples that can bend around buildings and travel over hills. Now go the other direction, faster than violet light, with tighter and tighter ripples. Just past violet is ultraviolet light. It is invisible to your eyes, but it is responsible for sunburn, the reason your skin turns pink after a long day outside. It is also the reason certain white shirts glow faintly under a black light at a party, because the ultraviolet light from the black light is absorbed by the fabric and then sent back out as visible light your eyes can see. Faster still are X-rays. These ripples are tight enough and energetic enough to pass straight through soft tissue like skin and muscle, which is exactly why doctors use them to see the solid bones underneath. The X-rays go through the soft parts and leave a shadow of the hard parts on the film or sensor behind. And faster still, the tightest, most energetic ripples of all are gamma rays. These are produced by some of the most violent events in the universe, exploding stars and the centers of galaxies, and they are also used, in tiny controlled amounts, in certain medical treatments, to target and destroy harmful cells in the body. All of these, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, are the exact same fundamental thing. They are all ripples of electric and magnetic fields, moving at the same universal speed, differing only in how tightly packed their ripples are. Together they are called the electromagnetic spectrum. And visible light, the only sliver your eyes can actually detect, is a tiny, tiny window in the middle of an enormous invisible landscape that surrounds you every moment of your life. Your eyes evolved to see this particular narrow slice because it happens to be the slice that passes most easily through Earth's atmosphere and the slice that the sun happens to produce most abundantly. It is not a coincidence that your eyes are tuned to exactly the kind of light the sun makes the most of. It is evolution quietly fitting your body to the world it was born into, matching the instrument to the available signal. Other animals see slightly different slices. Bees can see into the ultraviolet, which helps them find patterns on flowers that are completely invisible to us. Some snakes can sense infrared, which helps them find warm prey in the dark. But for us, the visible rainbow is what we were given, and it has been enough. Now let us talk about what happens when light actually meets an object, because this is where color, as your eyes experience it, comes from. This is one of those things that seems simple until you look at it closely, and then it becomes quietly beautiful. When light hits a surface, several things can happen to it. It can bounce off, which is called reflection. It can pass through and bend, which is called refraction. Or it can be soaked up and absorbed, its energy converted into heat, disappearing into the object and warming it very slightly. Almost every object you look at does a mixture of all three. It reflects some light, absorbs some light, and sometimes lets some light pass through. And the specific mixture, the specific combination of which colors bounce off and which colors get absorbed, is what determines the color you perceive when you look at that object. Here is the part that tends to catch people off guard. An object does not actually contain its color. A red apple is not red because something inside it is red. There is no red dye, no red paint, no red essence sitting in the skin of the apple. A red apple is red because when white light, made of all the mixed colors bundled together, hits its skin, the apple's surface absorbs almost every color except red. It soaks up the orange and the yellow and the green and the blue and the violet, converting them into a tiny bit of warmth, and it bounces the red part back out toward your eyes. The apple is really doing the opposite of containing red. It is rejecting every color except red. Red is the one color it will not keep. Color, in this sense, is less like a paint sitting on an object, and more like a decision the object makes about which light to keep and which light to send away. This is also why the same shirt can look like a slightly different color under fluorescent office lighting, warm lamplight, or outdoor sunlight. Each of those light sources contains a slightly different mixture of colors to begin with. Fluorescent light is heavier in blue and green. Lamplight is heavier in red and orange. Sunlight is the fullest mixture of all. So the shirt has different raw material to bounce back at your eyes each time, even though the shirt itself has not changed at all. The shirt is making the same decision about what to reject, but the menu of available light has changed, so the result looks a little different. Your eyes catch this bounced-back light using two kinds of cells packed into the back of your eye, on a thin layer called the retina. One kind, called rods, are extremely sensitive to dim light but cannot detect color at all. This is why the world looks mostly gray and colorless in very dim moonlight, even though your eyes are still working. The rods are doing their job, giving you a picture, but they do not carry color information, so the picture comes through in shades of gray. The other kind of cell, called cones, come in three types. Each type is tuned to respond most strongly to a different range of wavelengths, roughly matching red, green, and blue light. One cone type fires most strongly for reddish light. Another fires most strongly for greenish light. The third fires most strongly for bluish light. Your brain takes the signal strength from these three cone types and blends them together, the way mixing paint blends colors, to produce every shade you have ever seen. Millions of distinct colors, built from just three basic signals compared against each other. A bright yellow flower, for example, triggers your red cones and your green cones roughly equally, and your brain interprets that combination as yellow. It does not need a separate yellow detector, it just blends red and green. This is also why screens, phone screens, television screens, computer monitors are able to trick your eyes into seeing a full rainbow using only tiny red, green, and blue lights packed closely together. Your eyes do not need every wavelength individually. They just need the right ratio of those three signals, and your brain fills in the rest, believing it is seeing yellow or purple or turquoise, when really it is only ever receiving carefully balanced amounts of red, green, and blue. The entire world of color on a screen is a careful illusion, built to match the way your eyes already work. Now, one more piece of the mechanics, because it explains why a straw looks bent in a glass of water, and why a prism spreads light into a rainbow in the first place. Light does not travel at the same speed through every material. In empty space, in a vacuum, light travels at its absolute top speed, the full 186,000 miles per second. But when light enters a denser material, like water or glass or your own eyeball, it slows down slightly. It has to interact with the atoms packed into that material along the way, and those interactions take a tiny bit of time, slowing the overall progress. This slowing down causes the light to bend at the boundary where it enters the new material, the way a shopping cart with one wheel dragging in mud will veer off to one side. The side that hits the denser material first slows down first, and the whole beam pivots. Different colors of light, because they ripple at different frequencies, slow down by slightly different amounts inside the same material. Violet light slows down the most and bends the most. Red light slows down the least and bends the least. This tiny difference in bending is exactly what spreads white light into a full rainbow when it passes through a prism, or through raindrops hanging in the air after a storm. The colors were always there, bundled together, traveling as one. The bending just sorts them, sending each color off at a slightly different angle, so they arrive at your eye separately. That is the real mechanical secret behind every rainbow you have ever seen arched across the sky. There are two more pieces of the core mechanics worth understanding slowly, because they explain things you have noticed your whole life without ever quite knowing why. They are the reason the sky is blue, and the reason polarized sunglasses cut glare. But we will get to those shortly. For now, just let the basics settle. Light is a ripple of fields. Color is rippling speed. Objects reject colors they do not want. Your eye catches what bounces back, and your brain paints the world from three simple signals. It is simple, underneath, simple and quiet and true. Let that rest with you in the dark. The rest can wait. There is no hurry. The light is still traveling, and so is this night, and so are you. There are two more pieces of the core mechanics worth understanding slowly, because they explain things you have noticed your whole life without ever quite knowing why. These are the kinds of things that sit quietly in the background of everyday experience, so familiar that you stop seeing them until someone points out the reason behind them. And once you know the reason, you cannot help but see the world a little differently. The first is why the sky is blue during the day and why it turns orange and red at sunset. This is a question children ask, and it is a good one, because the answer is not obvious. The sky is just air, and air is invisible. So why does the air glow? Sunlight, as we have already learned, is a mixture of every visible color rippling together, all traveling as one. As that mixture passes down through Earth's atmosphere, it runs into countless tiny molecules of nitrogen and oxygen floating in the air. These molecules are far too small to reflect light the way a mirror does. A mirror is smooth and flat and bounces light back in a single clean direction. Air molecules are tiny and scattered, and they interact with light in a different way entirely. They scatter it. They take a tiny amount of the incoming light and bounce it off in a random new direction, almost like a pinball bouncing off a very small bumper. The light arrives from the sun traveling in one direction, hits a molecule, and gets sent off somewhere else. Here is the key detail, worked out by a British scientist named Lord Rayleigh in the 1870s, and it is the reason the sky looks the way it does. Tighter, faster rippling light, the blue and violet end of the rainbow, scatters far more easily off these tiny air molecules than looser, slower rippling light, the red and orange end. The blue light gets knocked around much more than the red light does. Violet light actually scatters even more than blue, but our eyes are naturally less sensitive to violet, and some of it gets absorbed high in the atmosphere before it can reach us. So what reaches your eyes, scattered down from every part of the sky, is mostly blue. That scattered blue light gets knocked around in every direction, bouncing from molecule to molecule, until it arrives at your eyes from every part of the sky at once. This is why the whole sky glows blue rather than just the direct spot where the sun sits. The blue light is not coming straight from the sun to your eye. It is coming from the sun, hitting the air somewhere above you, scattering sideways, and then reaching you from that new direction. Wherever you look in the daytime sky, you are seeing sunlight that has been redirected toward you by the air itself. At sunset, something changes. The sun is low on the horizon, and its light has to travel through a much longer stretch of atmosphere to reach your eyes. Instead of coming straight down through a relatively thin layer of air, it is coming in at a low angle, slicing through hundreds of extra miles of atmosphere. Over that much longer path, almost all of the blue light gets scattered away before it ever reaches you. It gets knocked off in every direction, scattered so many times that barely any of it survives traveling in a straight line all the way to your eyes. What is left, what actually makes it all the way through that long slanting path, is mostly the red and orange light, the colors that scatter the least and can push through the longest stretch of air relatively undisturbed. That is why sunsets glow warm and red, while the daytime sky glows cool and blue. It is the exact same physics, the exact same particles of nitrogen and oxygen, simply viewed through a different length of atmosphere. The sky has not changed. The air has not changed. The only thing that has changed is the angle of the sunlight and how much air it has to travel through to reach you. The same scattering that makes the sky blue during the day also paints the sunset in reds and oranges and pinks, simply by removing the blue and leaving the warmer colors behind. It is all one process, one quiet piece of physics, working differently depending on the time of day and where you happen to be standing. The second piece of the mechanics worth understanding is something called polarization, and it explains how certain sunglasses manage to cut glare so effectively. You have probably noticed this without thinking much about it. On a bright day, the glare off a wet road or a lake or the hood of a car can be harsh, almost painful to look at. But if you put on a pair of polarized sunglasses and tilt your head just slightly, the glare seems to melt away, and you can see through the reflection to the surface beneath. This is not magic. It is a clever use of a property of light that we have not yet talked about. Remember that light is a rippling of electric and magnetic fields, moving forward through space. The ripple itself, the wiggling of the fields, can happen in any direction that is perpendicular to the forward motion. Imagine the light traveling toward you in a straight line. The electric field can wiggle up and down, side to side, or at any diagonal angle in between. Ordinary sunlight is a jumbled mixture of ripples wiggling in every possible direction at once. Some waves wiggle vertically, some horizontally, some at every angle you can imagine. The light is unpolarized, meaning there is no preferred direction of wiggling. But when light reflects off a flat surface, something interesting happens. The reflection tends to filter out most of those wiggling directions, leaving mostly light that wiggles in one particular direction, usually horizontal, parallel to the surface it bounced off. The reflected light becomes polarized, aligned, all the ripples wiggling in the same plane. This is why glare off water, or a wet road, can be so blinding. It is not just bright, it is an unusually concentrated, aligned batch of ripples, all arriving at once, all wiggling in the same direction, hitting your eyes with a kind of sharp coherence that scattered light does not have. Polarized sunglasses contain a special film, a thin layer of material that acts, in effect, like a set of microscopic slits all lined up in one direction. This film only lets through light that is wiggling in the vertical direction, and it blocks most of the horizontal glare-heavy light. The scattered light from the rest of the scene, the trees and the sky and the road itself, is still mostly unpolarized, a jumble of all directions, so enough of it gets through the vertical slits to let you see clearly. But the harsh, horizontally polarized glare gets stopped almost completely. The result is that the glare disappears, or at least fades dramatically, while the rest of the world remains visible and clear. This is also, incidentally, why some polarized sunglasses can make certain phone screens or car dashboard displays appear to go strangely dark or show odd rainbow patterns when you tilt your head. Many modern screens produce their own light already leaning toward one particular polarization direction as a result of how the screen is manufactured. When you wear polarized sunglasses and tilt your head, you rotate the sunglasses filter, and if the angle of the filter lines up badly with the polarization of the screen, the light from the screen gets blocked. Tilt your head back the other way, and the screen brightens again. It is a small, everyday reminder that light is not just brightness and color. It has shape and direction to its ripples, a hidden geometry that we do not usually notice, but that is always there. That is the true core of how light behaves. A rippling of fields, electric and magnetic, moving at a universal top speed that never changes, slowed and bent differently by different materials, each color taking its own slightly different path, absorbed and reflected differently by different surfaces, each object making its own quiet decision about which colors to keep and which to send back, scattered by the tiny molecules of the sky itself, giving us blue days and red evenings, wiggling in directions that can be filtered and sorted, letting us cut through glare with a simple piece of film. Caught by 3 types of color-sensing cells at the back of the eye, and stitched together by the brain into the rich, colorful world you experience every waking moment. All of this is happening in the room around you right now. Even in the dark, even with your eyes closed, the same physics is quietly holding the universe together. The air is full of scattering molecules. The surfaces around you are making their decisions about what to absorb and what to reflect. Any faint light that happens to be present is wiggling in its own particular directions, carrying its own particular colors, traveling at its own unchangeable speed. The mechanics of light do not rest. They are constant, steady, always at work. And your own eyes, even closed, even in near darkness, are still doing their job. The rod cells, the ones sensitive to dim light but blind to color, are quietly active, adjusting, waiting, ready to catch the faintest scrap of light the moment there is any to catch. This is part of why a room never feels quite as pitch black after your eyes have had a few minutes to adjust as it did the instant you first turned off the lamp. Your rods are slowly ramping up their sensitivity, opening themselves to whatever faint light might be present, preparing to give you whatever picture they can, even if it is only a dim one in shades of gray. This is a good place to pause, to let the pieces settle. The sky is blue because the air scatters blue light more than red. Sunsets are red because the blue light has been scattered away by the long journey through the atmosphere. Polarized sunglasses work by filtering out the aligned glare bouncing off flat surfaces. Your eyes adjust to the dark by letting their most sensitive cells take over. These are not separate facts. They are all threads of the same fabric, the same underlying physics, the same rippling fields moving through space at the same constant speed. Everything is connected, underneath, in a way that is quiet and deep and true. So let your breathing stay slow, let the dark room hold you. The sky outside, whether it is blue or black or full of stars, is doing what it always does. The light is still traveling, still scattering, still carrying color and warmth and information across whatever distance it needs to cross. And you are here, receiving it, even with your eyes closed, even in the quiet of the night. There is nothing you need to do, nothing you need to remember. Just rest, and let the light do what it has always done. It will still be there when you wake. It has been patient for 14 billion years. It can wait a little longer. Let us move now into the different branches this idea grows into, the variations and extensions that came once scientists understood the basic mechanics of light. Once you know what light is, once you know it is a ripple of electric and magnetic fields moving at a fixed speed, you start to see that this single idea reaches out in many directions, like the branches of a tree spreading from a single trunk. Each branch is a different application, a different way the core understanding of light touches the world we live in. One of the biggest shifts in the whole history of light came at the very start of the 20th century, when scientists found that the wave picture of light, as complete and beautiful as it was, could not explain everything. Specifically, it could not explain something called the photoelectric effect. This was a puzzle that sat quietly in the background of physics for a little while, waiting for someone to look at it closely enough to see that it did not fit. Scientists had noticed that when light shines on certain metals, it can knock loose tiny electrons from the metal's surface, producing a small electric current. That much made sense under the wave picture. You could imagine the light waves arriving and shaking the electrons loose, the way a strong enough ocean wave might eventually shake a pebble free from a ledge. The energy of the light was being transferred to the electrons, giving them enough of a push to break free. So far, so good. But the details were strange, and they were strange in a way that the wave picture could not explain. If you made the light dimmer but kept its color the same, fewer electrons came loose. That part made sense. Less light, fewer electrons freed. But each electron that did come loose still flew off with the exact same energy as before. Dimming the light did not make the individual electrons weaker, it just made fewer of them appear. And if you switched to a color of light with a shorter wavelength, a tighter ripple, even a very dim beam of that color would knock electrons loose with much more energy than a bright beam of a longer wavelength. A bright red light might not knock any electrons loose at all, no matter how bright you made it, while a dim violet light would knock them loose easily, sending them flying off with considerable speed. Under pure wave thinking, this made no sense at all. More brightness should always mean more energy delivered, regardless of the color. A bigger wave should hit harder than a smaller wave. But that was not what was happening. The color of the light mattered more than the brightness. The frequency mattered more than the intensity. The wave picture, for all its elegance, could not account for this. Albert Einstein solved this puzzle in 1905. In the same remarkable year, he also explained several other deep mysteries in physics. His explanation brought back a piece of Newton's old particle idea, but in a completely new form, a form nobody could have predicted. Einstein proposed that light energy does not arrive smoothly and continuously, the way a wave washing onto a beach delivers its energy gradually, spread out over time and space. Instead, light arrives in small, discrete packets. These packets were later named photons. Each photon carries a specific, fixed amount of energy, and that amount is determined entirely by the color of the light, by its wavelength. A tightly rippling violet photon carries more energy per packet than a loosely rippling red photon, even if the red beam overall is much brighter, meaning it is delivering far more total packets per second. This explained everything about the photoelectric effect perfectly. Dimmer light of the same color means fewer photon packets arriving, so fewer electrons get knocked loose. But each successful hit still delivers the exact same fixed energy punch, because each photon of that color always carries that same fixed amount. The energy per packet does not change with brightness, only the number of packets changes, and a color with too little energy per photon simply cannot knock an electron loose at all, no matter how many billions of those weak photons you throw at the metal every second. Each individual hit is simply too gentle to do the job. It is like throwing 1,000 ping-pong balls at a locked door. They will never open it, even though one solid kick from a boot would. The energy per impact matters, not just the total number of impacts. So which was it then? Was light a wave, as Young and Maxwell had so carefully shown, spreading out and interfering with itself, bending around corners, producing those beautiful striped patterns on a screen? Or was light a stream of particle-like packets, as Einstein had now proven necessary to explain the photoelectric effect? The answer, confirmed by decades of further experiments throughout the 20th century, is that light is genuinely both. It depends on how you choose to look at it and measure it. This strange doubled nature is called wave-particle duality, and it remains one of the deepest and most genuinely strange truths in all of physics. Light spreads out and interferes with itself like a wave when it is traveling, when it is passing through slits or bending around obstacles. But light delivers its energy in discrete, particle-like packets when it is being absorbed or emitted, like at the surface of that metal, or inside the cells at the back of your eye, or inside a leaf capturing sunlight. It is not a wave sometimes and a particle other times, as if it changes costume depending on the occasion. It is something else entirely, something human language simply does not have a perfect word for. It displays wave behavior and particle behavior, depending on the situation, and both sets of behavior are real. Physicists eventually settled on simply calling this hybrid nature quantum behavior, and they built an entirely new branch of physics, called quantum mechanics, specifically to handle this strangeness, not just for light, but eventually for all matter. This quantum understanding of light opened up enormous practical branches of technology, extensions of the core idea that now surround your daily life, often without you ever having to think about them. Solar panels, for instance, work directly off the photoelectric effect that Einstein explained. They use sunlight's photon packets to knock electrons loose inside specially designed materials, generating usable electricity straight from sunlight striking a rooftop. The light arrives, packet by packet, and each packet that hits with enough energy frees an electron, and those freed electrons become an electric current you can use to power your home. Digital cameras work the same basic way in reverse of your eye. They use a grid of tiny light-sensitive sensors that convert incoming photons into an electrical signal, recorded and stored as a digital photograph. Each pixel on the sensor counts photons, and from those counts, the camera reconstructs the image you see on the screen. Lasers are another major branch worth understanding, because they reveal something extra about how light and atoms interact, a piece of the puzzle that goes beyond simple absorption and emission. Inside ordinary light sources, like a candle flame or a light bulb filament, atoms release photons randomly, in all different directions, at all slightly different moments. The result is light that spreads out messily in every direction and contains a whole mixture of colors and phases, uncoordinated and scattered. Inside a laser, atoms are carefully coaxed into releasing their photons all at exactly the same moment, all traveling in exactly the same direction, all at exactly the same wavelength, locked together in step, like a marching band moving in perfect unison instead of a crowd wandering randomly. This process, worked out through Einstein's own theoretical calculations decades before the first working laser was actually built in 1960, is called stimulated emission. A photon passing by an excited atom can trigger that atom to release its stored energy as a second photon, identical to the first in every way, same direction, same wavelength, same timing. That second photon can then trigger another atom and another, creating a cascade of identical photons all marching together. The result is a beam of light that stays remarkably narrow and focused over long distances, powerful enough to cut through steel in a factory, precise enough to correct the shape of a cornea during eye surgery, and gentle enough, in a very low-power form, to scan a barcode at a grocery store checkout. The same basic physics, scaled to different intensities, does all of these things. Fiber optic cables, the actual physical threads that carry most of the world's internet traffic under oceans and beneath city streets, are another extension of the core idea. They use the fact that light bends when it crosses between materials. Inside a fiber optic cable, light traveling through the thin glass core hits the boundary with the cable's outer coating at just the right angle to bounce back inward completely, every single time. This is called total internal reflection. The light cannot escape. It just bounces along, trapped inside the thin strand of glass, for hundreds of miles, carrying enormous amounts of information as rapidly blinking patterns of light. This very sentence, and every other piece of digital information moving around the world tonight, travels as pulses of light, racing along glass threads thinner than a human hair. The words you read, the voices you hear, the images you see, all of it rides on light, trapped in glass, crossing continents and oceans in fractions of a second. There is another extension worth knowing, one that reaches all the way out to the stars, and it is one of the quietest and most elegant applications of everything we have been talking about. Every different kind of atom, when heated enough to glow, releases light only at very specific, particular wavelengths. It is like a fingerprint made of color, rather than swirls of skin. No two elements have the same pattern. Hydrogen glows with one set of colors. Helium glows with another. Iron, oxygen, carbon, each has its own distinct pattern of bright and dark lines, a barcode written in light. A device called a spectroscope spreads incoming light out, much like Newton's prism did, but with far greater precision, revealing exactly which wavelengths are present and which are missing. In the 1850s, the German scientists Gustav Kirchhoff and Robert Bunsen, the same Bunsen whose name is attached to the gas burner still used in science classrooms, worked out that this fingerprint could identify exactly which elements were present in a glowing source, even one no human hand could ever touch. This is how astronomers know, with real confidence, what stars are made of, even though no telescope has ever physically visited one. Starlight itself carries the fingerprint of the elements burning inside, hydrogen, helium, and traces of heavier elements, encoded directly into the pattern of wavelengths present or missing when that starlight is spread out and examined carefully. It is also how astronomers first noticed that distant galaxies are rushing away from us. The entire fingerprint pattern from a moving light source shifts slightly, stretched toward the red end of the spectrum if the source is moving away, compressed toward the blue end if it is moving toward us. This shift, noticed in the light from distant galaxies, eventually revealed that the universe itself is expanding, that everything is moving apart from everything else, a quiet fact written in the color of ancient light. There is a much smaller, much more delicate branch of light worth mentioning too, one that happens not in stars or cables or lasers, but inside the bodies of living things. It is called bioluminescence, the ability some creatures have to produce their own light without any heat at all, through a careful chemical reaction happening inside their own cells. Fireflies produce a soft blinking glow in their tails, using a chemical called luciferin, combined with oxygen and a helper enzyme, releasing energy directly as light rather than warmth. The process is so efficient that almost none of the energy is wasted as heat, unlike a light bulb, which wastes most of its energy that way. Deep in the ocean, far below where any sunlight can reach, countless strange creatures produce their own light. Jellyfish that drift in the dark water, certain fish with glowing lures dangling in front of their mouths, tiny plankton that can make a wave appear to glow blue when disturbed at night. They all produce light for the same handful of reasons: to lure prey close, to startle a predator, or to find a mate in a world of permanent darkness. It is the same underlying physics as everything else we have talked about: atoms and molecules releasing energy as photons. It is just triggered by a careful chemical reaction rather than by heat or an electric current. The light is the same, the source is different, the physics is unchanged. Worth mentioning gently too is the branch of light having to do with how differently people can actually see it. Remember those 3 types of color-sensing cone cells in the retina, tuned roughly to red, green, and blue. In some people, usually men because of how the relevant instructions are carried on the chromosomes, one of those 3 cone types works a little differently than usual, or is missing entirely. This changes how certain colors, most commonly reds and greens, get blended together by the brain. This is what we call color blindness, though the name is a little misleading. It is not really an absence of seeing color. It is a difference in which particular blend of the same 3 signals a person's brain ends up working with. The world still has color. It is just mixed a little differently, seen through a slightly shifted set of filters. This is a reminder that the vivid, colorful world any one person experiences is, in a very real sense, being constructed privately inside their own skull. It is built from the same rippling light everyone else receives, the same photons arriving at the same speeds, but it is assembled slightly differently depending on the exact biological instrument doing the receiving. We all walk through the same world of light, but each of us sees a slightly different version of it. Not better or worse, just different, a private painting made from the same palette. There is a stranger branch still, one that grows directly out of the wave-particle duality we just walked through. Under certain special conditions, a single photon can be split into 2 new photons, whose properties stay connected no matter how far apart they later travel. This connection is called entanglement. Measure a property of one of these entangled photons here on Earth, and the paired photon, even if it has been sent to a satellite in orbit or across a city on a fiber optic line, will instantly show a matching, correlated result the moment it is measured too. Einstein himself was deeply uncomfortable with this idea. He called it spooky action at a distance, and he spent years trying to find a flaw in it, some hidden variable that would explain the correlation without requiring this strange instant connection across space. Decades of careful experiments since then, including work recognized with a Nobel Prize as recently as 2022, have confirmed that the effect is completely real. No hidden variable has been found. The connection is genuine, even though it still cannot be used to send an actual message faster than light, because of subtle limits on what the correlated results can actually tell you ahead of time. Engineers are now using entangled photons to build extremely secure communication lines, where any attempt to secretly listen in on the message actually disturbs the delicate entangled link and gets caught immediately. They are also building early versions of quantum computers, machines that use individual photons or other quantum particles as their basic unit of information, instead of the simple on-off switches used inside an ordinary computer chip. These machines are still in their infancy, but they represent a new kind of thinking, a new way of using the strangeness of light to do things that ordinary computers cannot. These are the branches: lasers and fiber optics, spectroscopy and bioluminescence, the quiet differences in how each pair of eyes sees the world, the strange connections of entangled particles. All of them grow from the same trunk. All of them are expressions of the same underlying reality. Light is a ripple of fields, moving at a fixed speed, carrying energy in discrete packets, bending and reflecting and scattering according to rules we now understand. And from that single understanding, 1,000 technologies and 1,000 insights have grown. Let these branches settle in your mind as you rest. They are not separate things to memorize. They are just different shapes of the same quiet truth, reaching out into the world in different directions, touching your life in ways you may not have noticed before. There is no need to hold on to any of it. Just let it be there, in the dark, like the light itself. Now let us bring this back to where you are, right now, tonight, because light is not some distant abstract topic locked away in laboratories or buried in textbooks. It is filling the room around you this very moment, doing dozens of quiet jobs at once, most of which you never have to think about. The whole story we have been walking through, From ancient Greece to quantum mechanics, from Ibn al-Haytham's dark room to Maxwell's dancing fields, all of it is happening right here, right now, in the space around your body, whether your eyes are open or closed. The screen you may have glanced at earlier tonight, before you settled into the dark, worked by exciting tiny red, green, and blue lights in precise patterns, tricking your three types of cone cells into perceiving millions of colors from just those three basic signals. That is all a screen ever does. It does not produce yellow light or purple light or any other color directly. It just lights up tiny red, green, and blue dots in different combinations, and your brain does the rest, blending them into every shade you have ever seen on a screen. The whole world of digital color is a careful collaboration between tiny lights and your own visual system, built on the fact that your eyes only need three signals to paint a full rainbow. If you are wearing glasses, or if you wear them during the day, the curved glass or plastic is bending incoming light on purpose, using exactly the refraction principle we talked about earlier. The lenses in your glasses are shaped to correct the way your own eyes bend light, compensating for an eye that is a little too long or a little too short, a cornea that curves a bit too much or a bit too little. The light enters the glass, slows down, bends at the boundary, and emerges traveling in a slightly different direction, so that by the time it reaches the lens inside your eye, it focuses cleanly on your retina, instead of a little in front of it or a little behind it. A quiet piece of shaped glass, carrying forward the same idea that Roger Bacon experimented with in the 13th century, the same idea that those first Italian craftsmen turned into the first eyeglasses, still doing its gentle work every single day. If there is a clock nearby with a glowing display, that soft glow is often produced by tiny diodes, small electronic components that release photons the moment an electric current passes through a specially engineered material. This is a modern, tiny, everyday cousin of the same stimulated emission that powers a laser, though far gentler and less focused. An electron jumps down from a higher energy level to a lower one, and as it does, it releases a photon. Multiply that by millions of tiny diodes, and you get the soft green or blue or red numbers glowing quietly on a bedside table, telling you the time without disturbing the dark too much. The warmth you feel from a blanket is not really about light directly, but the warmth radiating off your own body right now, and off anyone or anything warm nearby, is a form of light. It is infrared light, invisible to your eyes but completely real, constantly leaving your skin as a soft, quiet glow. This is the same kind of light we talked about earlier, sitting just below red on the electromagnetic spectrum, too slow rippling for your eyes to catch, but perfectly detectable by your skin as warmth. If you could see in infrared, you would notice your whole body glowing gently in the dark, a slow, steady radiance leaking out of you every second of every day, simply because you are warm. Warm things always emit light your eyes cannot see. You are a source of light right now, quietly shining into the room in a color no one can see. Somewhere nearby, Wi-Fi signals are crossing the room right now, carrying data as a form of light far too loose and slow rippling for your eyes to catch. But it is the same family, the same electromagnetic spectrum, just tuned to a different frequency. These waves pass silently through walls and through you, constantly, without you feeling a thing. The words you might have read earlier, the messages you might have sent, the music you might have listened to, all of it traveled through the air as light. Just light of a kind your eyes were never built to notice. The internet, so much of it, is light moving through the air or through glass fibers, carrying the weight of human conversation and human knowledge on ripples of electric and magnetic fields. Outside, if it is a clear night and you happen to have a window nearby, starlight is arriving after unimaginable journeys. Some of that light left its star thousands or even millions of years ago, long before there were any humans to see it, long before the Earth had formed into the shape it holds now. Some of what a person might see looking up tonight is a kind of memory, an old photograph of a star as it once was, possibly changed, possibly even gone by now, the light simply still finishing its long trip toward Earth. The star itself may have died, collapsed, faded into a cold cinder, but its light is still traveling, still arriving, still landing quietly on rooftops and treetops and closed eyelids. You are always looking back in time when you look at the night sky. The deeper you look, the further back you see. Even moonlight is really just sunlight, bounced off the moon's dusty gray surface and redirected down toward you. The moon does not make its own light. It is a mirror, a pale, dusty mirror hanging in the sky, catching the light that left the sun 8 minutes earlier and sending a small fraction of it down to Earth. That moonlight arrives a little over a second after leaving the moon, carrying warmth and brightness from a source 93 million miles further away still. When you stand in moonlight, you are standing in reflected sunlight, twice traveled, once from the sun to the moon, and once from the moon to you. If it happened to rain sometime today, and the sun came out again afterward, you may have caught sight of a rainbow arching across the sky, and now you know exactly what was happening inside each of those countless falling raindrops. Sunlight was entering each droplet, slowing down and bending as it crossed from air into water, exactly the way it bends crossing into Newton's glass prism. The light split into its full range of colors inside the droplet, each color bending by a slightly different amount. That light then bounced once off the inside back wall of the droplet, curving around, and bent again on its way back out into the air, spreading the colors even further apart in the process. Every single raindrop hanging in the air is doing this at once, a sky full of tiny prisms, each one sorting sunlight into its hidden colors. The specific angle at which red light versus violet light manages to reach your particular eyes, out of the millions of droplets scattered across the sky, is what carves out the familiar curved band of color. A rainbow always appears exactly opposite the sun from wherever you happen to be standing. This is why you can never walk up to the end of a rainbow. It is not sitting at a fixed spot in the world at all. It is a pattern built freshly, in that instant, out of the precise angle between the sun, the rain, and your own two eyes. Move a few steps to the left, and the rainbow moves with you. It is not an object, it is a relationship, a geometry of light and water and position, and it exists only for the person seeing it. Someone standing a few feet away is seeing a different rainbow, built from different droplets, bent at slightly different angles, just for them. If anyone in the house has ever had an X-ray taken at a doctor's office, that image was built using the highest energy, tightest rippling end of the spectrum that sits just past visible light. The X-rays we talked about earlier pass easily through soft tissue like skin and muscle, but they get partly blocked by the denser calcium packed into bone. The result is a shadow-like picture of the skeleton on the film or digital sensor behind. A photograph taken with light that can see through the soft parts of you. It is the same physics as a visible light photograph, the same principle of absorption and transmission, just at a much tighter, more energetic ripple. The light goes through what it can, gets stopped by what it cannot, and leaves a record of the difference. And if a house nearby has a security camera that somehow still shows a clear picture in near total darkness, it is very likely using a ring of small infrared lights around its lens. These lights are invisible to human eyes, glowing in a color we cannot see, but they are bright and obvious to the camera's sensor, which is built to detect exactly that range of wavelengths. The camera quietly floods the space with a kind of light nobody in the room can see, and then it watches by that invisible illumination, turning infrared reflections into a visible image on a screen somewhere. The night is never truly dark to a camera that can see infrared. It is full of light we simply were not built to notice. And under your closed eyelids right now, if you are lying in a dark room, your rod cells are still quietly active. They are adjusting, waiting, ready to catch the faintest scrap of light the moment there is any to catch. This is part of why a room never feels quite as pitch black after your eyes have had a few minutes to adjust, as it did the instant you first turned off the lamp. Your rods are slowly ramping up their sensitivity, opening themselves to whatever faint light might be present. They are the most sensitive light detectors in your body, able to respond to a single photon under the right conditions, a single packet of light arriving out of the darkness. In near total darkness, you might notice faint, shapeless glimmers, tiny flashes of light that seem to come from nowhere. Some of these are just the random firing of cells in your retina, but some may actually be individual photons, single packets of light, triggering a rod cell all on their own. You are, in those moments, seeing light at the smallest possible scale, one packet at a time. All of this is happening around you right now. The infrared glow of your own body, the Wi-Fi light passing through the walls, the starlight arriving from years or centuries away, the moonlight that is really sunlight, making a second journey, the rods in your eyes slowly adjusting to the dark, waiting for something to see. The physics we have been walking through all night is not abstract. It is the room you are lying in. It is the warmth on your skin. It is the faint glow of a clock, the screen you looked at earlier, the glasses on your bedside table. Light is doing all of this, quietly, constantly, without ever asking for your attention. So just lie there and let it be. You do not have to do anything with this knowledge. You do not have to hold on to it or remember it or even stay awake for it. The light will keep doing what it does, whether you are watching or not. It has been doing this for 14 billion years. It will keep doing it long after tonight is over. You are just here for a little while, lying in the middle of all that quiet traveling light, and that is enough. Let your breathing stay slow. Let the warmth of your own body remind you that you too are a source of light, glowing softly in a color no one can see. The night is full of light you cannot see, and that is not a lack. It is just a wider world, waiting quietly beyond the edges of your senses, and you are part of it, whether you know it or not. Now let us talk gently about the harder questions, the parts even the scientists who study light for their entire careers still find strange and unresolved. There is something comforting about knowing that not everything needs to be fully solved to be beautiful. A mystery does not have to be a problem. Sometimes it is just a quiet edge of what we understand, a place where the map fades into blank space, and that blank space is not a failure. It is an invitation to rest, to accept that some things are still open, still unfolding, still waiting for a mind patient enough to sit with them. One of the strangest unresolved puzzles concerns exactly what a photon is between the moment it is released and the moment it is absorbed. We know what happens at the beginning and at the end. An electron in an atom jumps down from a higher energy level to a lower one, and a photon is born, carrying away the spare energy. That photon travels across whatever distance it must cross, and then it arrives at another atom, where it is absorbed, giving its energy to a new electron, which jumps up to a higher level. The beginning is clear, the end is clear, but what is the photon doing in between? Does it travel as a spread-out wave the entire time, a ripple of electric and magnetic fields expanding outward, only somehow becoming a single point-like particle at the very last instant of being detected? Physicists can predict, with extraordinary mathematical precision, the probability of where a photon will be found when someone finally looks for it. The equations of quantum mechanics give numbers that match experiments to many decimal places, a level of accuracy that is almost unheard of in any other field of human knowledge. But the deeper question, what a photon is actually doing while nobody is looking, remains a subject of real debate. This is sometimes called the measurement problem in quantum mechanics, and it sits at the heart of a puzzle nobody has fully solved, despite a century of the most careful thinking. Before a measurement is made, the photon seems to exist in a kind of spread-out possibility, a wave of potential locations, none of them definite. The moment a measurement happens, the photon appears at one specific point, as though the wave suddenly collapsed into a single place. What causes that collapse? Is it the act of measurement itself? Does the photon somehow choose a location? Or is there something else going on, something we have not yet understood? Different physicists give different answers, and none of the answers commands universal agreement. The photon, the simplest piece of light there is, still holds a quiet mystery at its core. There is also the strange fact that light seems to take every possible path between 2 points at once, cancelling most of them out through interference, until only the most efficient path survives. This idea is captured by a piece of physics called the principle of least action, first properly formalized by the French mathematician Pierre de Fermat in the 17th century and later expanded by others. Fermat noticed that light always travels between 2 points along the path that takes the least time. If the light has to go through different materials, it bends at the boundaries in exactly the way that minimizes the total travel time. This is why a straw looks bent in a glass of water, and why a lens can focus light to a point. The light is simply finding the fastest route. But how does the light know which path is fastest before it has traveled it? In a very real sense, a beam of light behaves as though it somehow checks every possible route before committing to the one that takes the least time. In the quantum picture, you can think of the light as actually taking all possible paths at once, with most of those paths cancelling each other out through interference, the same kind of adding and cancelling that Young saw in his two-slit experiment. The only path that survives all that cancelling is the one where the light arrives in step with itself, and that path happens to be the fastest one. It is a beautiful and strange idea, and it raises deep, still not entirely settled questions about the nature of time and causation at the smallest scales of reality. Does the light somehow know the future? Or is our ordinary idea of cause and effect simply not quite right at the quantum level? These are not questions with easy answers. They are questions to sit with, in the dark, letting the strangeness of them wash over you without needing to resolve anything. Then there is the question of light and gravity, something Einstein himself worked out a decade after his photoelectric paper with his theory of general relativity. Light, despite having no mass in the ordinary sense, is still bent by the gravity of massive objects. This is because gravity, in Einstein's picture, is not really a pulling force at all. It is a curving of space and time themselves. A massive object like the sun or a planet bends the space around it, the way a heavy ball placed on a stretched rubber sheet makes a dip that causes smaller balls to roll toward it. Light, like everything else, simply follows the curves it finds. It travels in straight lines through curved space, and a straight line through curved space looks like a bend to an outside observer. This was proven dramatically in 1919, when astronomers measured starlight bending visibly around the sun during a total solar eclipse. The stars near the sun appeared very slightly shifted from their usual positions because their light had been bent by the sun's gravity on its way to Earth. The shift matched Einstein's predicted numbers exactly, turning him overnight into one of the most recognized scientists in the world. Light, which had seemed so separate from gravity, so weightless and indifferent, was actually following the shape of space itself, obedient to the same deep geometry that holds planets in their orbits. Around a black hole, gravity curves space so extremely that light cannot escape at all once it crosses a certain boundary, the event horizon. This is the literal reason black holes appear black. They are not empty. They are full of matter, crushed to an extraordinary density, and the space around them is curved so steeply that even light, the fastest thing in the universe, cannot climb back out. It falls inward, forever, trapped inside a curve from which there is no return. Light, for all its speed, for all its untouchable nature, can be caught. Gravity can hold it, bend it, redirect it, and in the most extreme cases, swallow it whole. There is also a strange twist on Young's original two-slit experiment that still unsettles people who hear about it for the first time. Remember that when light passes through two narrow slits, it produces a striped interference pattern on the screen behind, the signature of wave behavior. But if you set up detectors to quietly check which of the two slits each individual photon actually passed through, something odd happens. The striped interference pattern vanishes completely. The light suddenly behaves exactly like simple particles again, landing in just two clumps behind the slits, as though the wave nature had never been there at all. Simply observing which path the light took, even gently, even without disturbing it very much, is enough to collapse the wave-like behavior back into particle-like behavior. The mere act of knowing which slit the photon went through changes what the photon does. It is as if the light cares whether it is being watched. This is not magic, it is a consequence of how measurement works at the quantum level. But it is genuinely strange, and it has been confirmed in experiment after experiment for decades. Even stranger, physicists have run versions of this experiment where the decision to check which path was taken is made after the photon has already passed through the slits. This is called the delayed choice experiment, first proposed by the physicist John Wheeler. You might think that once the photon has passed through the slits, what it did back there is settled. But the results come out the same way. If you decide to check which slit it went through, even after it has already passed through, the interference pattern vanishes. If you decide not to check, the interference pattern remains. It is as though the photon's earlier behavior somehow depends on a choice made after the fact, as though the past is not as fixed as we ordinarily believe. This puzzle remains genuinely unresolved and continues to be debated and retested by physicists today. It is worth mentioning too where the whole idea of light arriving in discrete packets first came from, just before Einstein picked it up. A few years earlier, in 1900, a German physicist named Max Planck was trying to solve a completely different, more practical puzzle. He wanted to explain why glowing hot objects, like a heated piece of metal or the filament inside a light bulb, give off the specific mixture of colors they do at each particular temperature. As an object gets hotter, its glow shifts from a dull red to a brighter orange, and eventually to a brilliant white. The wave picture of light, worked out so beautifully across the 1800s, kept predicting an impossible, infinite amount of energy at the tightly rippling end of the spectrum. This breakdown was nicknamed the ultraviolet catastrophe, and it was a clear sign that something was wrong with the theory. Planck found that the only way to make the mathematics match what was actually observed in real glowing objects was to assume that light energy could only be given off in small, fixed-size chunks, rather than smoothly and continuously. He called these chunks quanta, from the Latin word for how much. Planck himself considered this more of a useful mathematical trick than a statement about how reality truly worked. He was a cautious man, and he did not want to claim more than his equations could support. It took Einstein's photoelectric explanation 5 years later to argue that these chunks, these quanta, were not just a convenient trick, but a real, physical feature of light itself. Planck lived to see his cautious mathematical patch become one of the deepest true statements about the nature of reality, which is its own kind of quiet, strange story. A man who set out to fix a small problem in the theory of hot objects ended up opening the door to quantum mechanics. And there is the deepest, quietest mystery of all, sitting underneath everything else we have talked about tonight. From light's own perspective, if you can even meaningfully imagine such a thing, no time passes at all between being emitted and being absorbed, anywhere, no matter the distance. Einstein's own equations suggest that for something traveling at the speed of light itself, time simply stops entirely. A photon does not experience the passage of time. It is born in a star, and it arrives at your eye, and those two events, for the photon, are the same instant. The millions of years of travel across the empty spaces between galaxies, for the photon, are not years at all. They are nothing. A single, timeless moment, connecting the star that made it to the eye that catches it. Every photon that has ever traveled from every star, across every unimaginable distance, in some strange mathematical sense, experiences its entire multi-million-year journey as a single instant, with no duration, no before and after. The photon is not patient, because patience requires time, and the photon has none. It is not in a hurry, because hurry also requires time. It simply is, connecting one event to another, with nothing in between from its own point of view. Physicists still debate exactly how meaningful it is to talk about a photon's own point of view at all, since the normal rules of experience seem to break down completely at that speed. A photon has no mass, no rest frame, no clock that can tick. Trying to imagine what the world looks like from a photon's perspective may be like trying to imagine a color you have never seen. The very idea of perspective may not apply. It remains one of the strangest, quietest edges of what we understand, and it is a comfortable kind of not knowing to rest inside tonight. These are the harder questions. What is a photon doing when no one is looking? How does light know the fastest path before it travels it? How can gravity bend something that has no mass? Why does watching a photon change what it does? How can a choice made now seem to affect something that happened earlier? And what does it mean that for light itself, no time ever passes at all? None of these questions have final answers. They are still open, still being thought about, still being tested in laboratories and debated in lecture halls. And that is all right. Not everything needs to be settled. Not everything needs to be understood completely. There is a kind of peace in knowing that the world is still larger than our understanding of it, that light still holds mysteries after all these centuries of careful study. You can lie in the dark and let those mysteries be mysteries. They do not need you to solve them. They are just there, like the light itself, quiet and patient and full of depth. Let that be enough. Let the not knowing be a soft place to rest, not a problem to fix. The night is full of questions that do not need answers, and you are allowed to simply be here, in the middle of them, breathing slowly, letting them drift past like warm water, like the light from a street lamp on a curtain, like everything else that has been traveling quietly through the dark. By now you may have drifted in and out a few times. That is exactly right. There is nothing to catch up on. Everything has been settling quietly whether you were following closely or not, the way sound settles into a room even if you were not listening for it. The words have been here, and some of them may have landed, and some of them may have passed by, and both of those things are fine. You do not need to gather them all up. You do not need to hold on to any of them. The ideas will still be here if you want to come back to them later, and if you do not, that is all right too. If you were to hold all of tonight in one single image, a single picture that gathers together everything we have walked through, it would be this. A single unified rippling of electric and magnetic fields, moving through space at a speed that never changes. That is what light is, at its core. That is the simple truth underneath all the history and all the experiments and all the names we have spoken tonight. This one rippling thing was born from ancient people wondering whether their eyes reached out or simply received, a question that sat at the center of human thought for 2,000 years before Ibn al-Haytham finally tested it and found the answer. Light arrives. It does not reach out from us. It comes to us, traveling in straight lines, bringing the world to our eyes without us having to do anything at all. This one rippling thing was sorted properly by Newton's careful use of 2 glass prisms in a darkened countryside room. He showed that white light is not pure and simple, but a mixture of all the colors bundled together, and that a prism does not create color, but simply reveals what was already there, hidden inside the white, waiting to be seen. Red bending the least, violet bending the most, and every other color finding its place in between. This one rippling thing was proven to ripple like a wave by Young's simple striped pattern, a piece of card with 2 slits and a candle flame, producing bands of bright and dark that only waves can make. Light overlaps with itself. It cancels and reinforces. It bends around edges and spreads out through narrow openings. It behaves not like tiny bullets, but like ripples on a pond, spreading and meeting and dancing together in patterns we can see and measure and predict. This one rippling thing was unified with electricity and magnetism by Maxwell's elegant mathematics, 4 equations that showed these 2 forces are really one, and that light itself is the expression of their dance. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They chase each other forward, endlessly, needing no medium, needing nothing but themselves, moving at exactly the speed we had already measured for light. This one rippling thing was revealed to also travel in discrete, countable packets by Einstein's explanation of a strange electrical puzzle. The photoelectric effect showed that light energy arrives not as a smooth, continuous wave, but in small, fixed chunks, photons, each one carrying a specific amount of energy determined by its color. Dimmer light means fewer photons, not weaker ones. A tighter ripple means more energy per photon. The wave picture and the particle picture, which had seemed opposed for so long, turned out to be two faces of the same deeper truth. And this one rippling thing was finally understood as something genuinely, comfortably strange. A wave and a particle at once, depending only on how carefully and how closely you choose to look. Not one thing or the other, but something that human language does not have a perfect word for. Something that spreads out like a ripple when it travels and lands like a packet when it arrives. Something that seems to take every possible path at once, and somehow chooses the fastest one. Something that, from its own perspective, experiences no time at all between being born and being absorbed, no matter how far it travels. That one rippling thing, unimaginably fast, unimaginably old in the case of starlight, is the same thing letting you see these words if you are reading them. The same thing that has been warming your skin all night. The same thing carrying your Wi-Fi signal through the air around you right now, passing silently through walls and through you, constantly, without you feeling a thing. The same thing powering the plants that eventually became your dinner. Sunlight caught by leaves and turned into chemical energy that flowed up through the food chain until it reached your plate. The same thing quietly filling the dark room around you right now, whether your eyes are open or closed. It is all one thing: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. All of it is the same fundamental ripple, the same dance of electric and magnetic fields, differing only in how tightly packed the waves are. The visible rainbow, the only sliver our eyes can detect, is a tiny window in the middle of an enormous invisible landscape that surrounds us every moment of our lives. We are swimming in light we cannot see, and that is not a lack. It is just a wider world, waiting quietly beyond the edges of our senses. It began with a question about eyes and fire, thousands of years ago, in cultures that had no idea the answer would take this long or lead this far. It led into space itself curving, into particles that check every path at once, into a signal crossing an ocean floor as a blink of light to bring you this very sentence. From a dark room in ancient Basra, to a dark room in 19th century Paris, to the fiber optic cables crisscrossing the ocean floor, the story of light is the story of humans paying attention, asking questions, testing answers, and slowly, patiently, over centuries, coming to understand something true. And that understanding does not diminish the mystery, it deepens it. Knowing that a rainbow is sunlight sorted by raindrops does not make a rainbow any less beautiful. Knowing that the blue sky is scattered light does not make the sky any less deep. Knowing that starlight is ancient and that moonlight is twice reflected sunlight and that your own body glows in infrared does not make the night any less quiet or any less full of wonder. It just adds layers. It gives you more to rest inside. So let it settle now, the way it always has. The way it did for the first candle ever lit in a cave. A flame pushing back the darkness for the first time, and someone looking at that flame and wondering what it was, where the light came from, how it reached their eyes. The way it does for a screen glowing quietly nearby right now, a screen that works by tricking your 3 types of cone cells with tiny red, green, and blue dots, just as your eyes have always been tricked, just as the world has always been built from simple signals blended into a rich and colorful whole. The way it does for a star whose light left home before there were any humans at all to receive it, traveling across millions of years of empty space, arriving exactly now, exactly here, touching your closed eyelids or your skin, or the blanket pulled up around you. Somewhere above you, even through a ceiling, even through clouds, there is light still traveling, patient, steady, arriving exactly on time no matter how long the trip took to get here. The light from the moon, which is really sunlight making a second journey. The light from distant stars, which is a kind of memory, an old photograph of a star as it once was. The light from galaxies so far away that their glow has been stretched toward the red end of the spectrum by the expansion of the universe itself. All of it traveling, all of it arriving, all of it part of the same single dance. Your body is warm right now, and some tiny sliver of that warmth is quietly leaving you too. It is drifting outward into the dark room, into the night, joining everything else that is simply, quietly, endlessly traveling. You are a source of light. You have been a source of light your whole life, glowing softly in a color no one can see. Your warmth, your presence, your quiet breathing in the dark, all of it radiates outward, mingling with the light that is already here, becoming part of the great quiet ocean of electromagnetic waves that fills the world. Let your breathing slow to match it. Let the rhythm of your breath find the rhythm of the light, steady and patient and unhurried. There is nowhere else that light needs to be. It has already arrived. It is already here, filling the room, touching your skin, waiting for nothing, rushing for nothing. And there is nowhere else you need to be either, not tonight. You are exactly where you are supposed to be, lying in the dark, in the middle of all that quiet traveling light. You do not have to hold on to any of this. You do not have to remember the names or the dates or the details, the Pythagoreans and their I-beams, Ibn al-Haytham and his dark room, Newton and his prisms, Young and his two slits, Maxwell and his equations, Einstein and his photons. All of them did their work, and their work is done, and now it is just here, part of the world, part of what we know, part of what we can rest inside. The light does not need you to remember how it works. It just works. It just travels. It just arrives. So just rest now, here, in the dark, in the middle of all that quiet traveling light. Let the warmth of your own body remind you that you are part of this too, a small glow in the vast electromagnetic sea, connected to everything else by the same physics, the same fields, the same constant speed. The light has been patient for 14 billion years. It will keep being patient long after tonight is over, and you are allowed to be patient too. You are allowed to rest. You are allowed to let go of everything you have been carrying and simply be here, breathing slowly, letting the light do what it has always done. There is nothing you need to do, nothing you need to figure out, nothing you need to become. You are already here, already receiving, already glowing. The messengers are still landing on your skin, tiny packets of light that have traveled unimaginable distances to reach you. You have never once touched one, and you never will, but they touch you, constantly, gently, without asking for anything in return. Let that be enough. Let that be everything. Let yourself finally, fully drift off to sleep. So let it settle now, the way it always has. The way it did for the first candle ever lit in a cave. A small flame pushing back the darkness for the first time, and someone sitting near that flame, watching the shadows dance on the walls, wondering what the light was and how it reached their eyes. They did not have the words for photons or electromagnetic fields. They did not know about wavelengths or the speed of light, or the rods and cones at the back of the eye. But they sat in the flickering glow, and they wondered, and that wondering was the beginning of everything we have walked through tonight. Let it settle the way it does for a screen glowing quietly nearby right now. A screen that works by lighting up tiny red, green, and blue dots in careful patterns, tricking your 3 types of cone cells into seeing a full rainbow that is not really there. The screen does not make yellow light. It does not make purple or turquoise or any of the 1,000 shades you might see on it. It only makes red, green, and blue. Your brain does the rest, blending those 3 simple signals into a world of color, just as it has always done, just as it does with the real world outside the screen. The same 3 signals, the same quiet process, stitching together the rich and varied tapestry of everything you have ever seen. Let it settle the way it does, for a star whose light left home before there were any humans at all to receive it. That light has been traveling across the empty spaces between stars for millions or even billions of years, a quiet ripple of electric and magnetic fields moving at the same constant speed, never slowing, never stopping, never asking for anything. And now it arrives. Now it reaches the ceiling above you, or the window beside you, or the thin skin of your closed eyelids. It completes its journey in this moment, in this room, with you. The star that made it may be gone. It may have burned out and faded and collapsed into a cold cinder drifting through space. But its light is still here, still traveling, still arriving, a memory made of rippling fields, older than the earth itself, touching you now in the quiet of the night. Somewhere above you, even through a ceiling, even through clouds, there is light still traveling, patient, steady, arriving exactly on time no matter how long the trip took to get here. The light from the moon, which is really just sunlight that bounced off a dusty gray surface and made a second journey across the void. The light from distant planets, faint and steady, carrying the colors of their atmospheres encoded in the spectrum, if anyone were there to read it. The light from galaxies so far away that their glow has been stretched and shifted by the expansion of the universe itself, arriving not as it was when it left, but as something slightly different, slightly redder, slightly older, changed by the very shape of space and time through which it traveled. Your body is warm right now, and some tiny sliver of that warmth is quietly leaving you too. It is drifting outward into the dark room, into the night, joining everything else that is simply, quietly, endlessly traveling. You are a source of light. You have been a source of light your whole life, glowing softly in a color no one can see, a gentle infrared radiance that leaks from your skin every second of every day. If someone could see an infrared, they would see you glowing in the dark, a warm and steady presence, a small sun in the shape of a person. And that light leaves you and travels outward, mixing with the light from the stars and the moon and the screen and the clock on the bedside table, all of it part of the same great quiet ocean of electromagnetic waves that fills the world. Let your breathing slow to match it. Let the rhythm of your breath find the rhythm of the light, steady and patient and unhurried. There is nowhere else that light needs to be. It has already arrived. It is already here, filling the room, touching your skin, waiting for nothing, rushing for nothing. It has crossed millions of miles or just a few feet, and now it is here, and that is enough. The journey is complete. The message is delivered. The light does not need you to see it or acknowledge it or even be awake for it. It just is. It just arrives. It just rests here with you, in the dark, in the quiet, in the warmth of your own body. And there is nowhere else you need to be either. Not tonight. You are exactly where you are supposed to be, lying in the dark, in the middle of all that quiet traveling light. You do not have to hold on to any of the words we have spoken. You do not have to remember the names or the dates or the details. The Pythagoreans and their reaching eye-beams, wondering if sight was something active, something sent out from the eye like invisible hands. Ibn al-Haytham and his dark room, proving with careful logic that light arrives, that it travels from the world into the eye, not the other way around. Newton and his prisms, sorting white light into its hidden colors and showing that the rainbow was always there, waiting inside the whiteness. Young and his two slits, proving with a piece of card and a candle that light is a wave, that it overlaps and cancels and makes patterns that only ripples can make. Maxwell and his equations, showing that light is electricity and magnetism dancing together, needing no medium, needing nothing but themselves, moving at a speed that never changes. Einstein and his photons, bringing back the particle idea in a new form, showing that light energy arrives in packets, each one carrying a fixed amount determined by its color, each one a tiny messenger traveling across whatever distance it must cross. All of them did their work. All of them asked their questions and tested their answers, and added their piece to the great slow puzzle of understanding what light actually is. And now their work is done, and it is just here, part of the world, part of what we know, part of what we can rest inside. The light does not need you to remember how it works. It just works, it just travels, it just arrives. It has been doing this for 14 billion years, since the very first moment of the universe, when everything was hot and dense and full of light, and it has been traveling ever since, cooling and spreading and filling the expanding space with its quiet presence. You are part of this too. You always have been. The same physics that guides the light from a distant star guides the light that left your body a moment ago, drifting outward into the room. The same fields that ripple through space ripple through you. The same constant speed that carries starlight across millions of years carries the warmth of your skin to the blanket pulled up around you. You are not separate from this story. You are in it, of it, part of it. A warm and glowing presence in the vast electromagnetic sea, connected to everything else by the same quiet rules, the same gentle physics, the same unchangeable speed. So just rest now, here, in the dark, in the middle of all that quiet traveling light. Let the warmth of your own body remind you that you are still here, still breathing, still glowing. Let the darkness around you feel not like an absence but like a presence, full of light you cannot see, full of signals and warmth and ancient starlight, all of it passing through you and around you, all of it part of the same single dance. You do not have to do anything. You do not have to figure anything out. You do not have to become anything other than what you already are. You are already here, already receiving, already glowing. The messengers are still landing on your skin, tiny packets of light that have traveled unimaginable distances to reach you, from the moon, from the stars, from the lamp on the ceiling, from your own warm body reflected back off the blankets. You have never once touched one of these messengers, and you never will. They are untouchable, weightless, massless, moving at the fastest speed the universe allows. But they touch you, constantly, gently, without asking for anything in return. Let that be enough. Let that be everything. You are lying in the dark, in the middle of all that quiet traveling light, and there is nothing you need to do, nothing you need to remember, nothing you need to hold on to. The light will keep traveling whether you are awake or asleep. It will keep arriving whether you are watching or not. It has been patient for 14 billion years. It can wait for you a little longer. It can wait while you breathe, while you rest, while you let go of the day and the thoughts and the names and the dates. Let yourself finally, fully, drift off to sleep. Let the rhythm of your breathing slow and deepen. Let the warmth of the blankets hold you. Let the quiet of the room wrap around you like a soft and familiar weight. The light is still here. It will still be here when you wake. It will still be traveling, still arriving, still bringing the world to your eyes the moment you open them. And you will be here too, rested and warm, ready to receive it. But that is for the morning. Tonight is for resting. Tonight is for letting go. Tonight is for being exactly where you are, in the dark, in the quiet, in the middle of all that quiet traveling light. There is nowhere else you need to be. There is nothing else you need to do. Just rest now. Just breathe. Just let the light do what it has always done, and let yourself do what you have always needed to do, which is simply to rest, to let go, to drift slowly and gently into sleep. The light is patient, the night is long, and you are safe here, in the dark, in the quiet, in the warmth, with the messengers still landing softly on your skin, asking nothing, needing nothing, just arriving, just being here, just like you. So sleep now, sleep deeply, sleep well. The light will keep watch. It always has, it always will.